Alrighty, folks, so let's move into lesson 2 for the trigonometry unit here. We're going to start actually looking at doing trigonometry, right? Good old SOHCAHTOA and all that fun stuff, our actual trigonometric ratios, and evaluating those ratios for angles in standard position. And now from after the previous lesson, we can also work with radians and angles measured that way. So as always, there's a little checklist you can kind of use to see at the end of the lesson, right? How are you feeling about those big ideas? And yeah, let's jump right in. All right, so as you kind of know, and as we brought up in the previous lesson, okay, in order to do like trigonometry, what we're often doing, right, is taking ratios, that SOHCAHTOA, sine, cos, and tan, right, which are ratios of sides in a triangle, right, the opposite side over the hypotenuse, so, or adjacent over hypotenuse, ka, or opposite over adjacent for tan, right, toa, SOHCAHTOA, right? So again, that's referring to like a triangle, a right angle triangle. Opposite to what? Opposite to the angle within a triangle, right? The hypotenuse of a right angle triangle, adjacent to an angle within a triangle. And so in order to be able to do this trigonometry with these angles in standard position, recall that we need those reference triangles. Sorry, there's sirens going on outside my house. Hope that's not too loud. Okay, so every angle in standard position has a reference triangle, as shown in these diagrams down here. We kind of talked about them a little bit in the previous lesson as well, right? You've got your angle in standard position. You can think about a reference angle there, and really one of the main points of thinking about a reference angle is so that you can draw this reference triangle here and start actually doing some trig with it, doing what's the opposite or the adjacent or the hypotenuse with that reference angle, right? That reference triangle is the triangle we'll use with our reference angle in order to actually do trig with an angle in standard position. And that reference triangle can be used to write the primary trig ratios. The primary trig ratios are just SOHCAHTOA, sine, cos, and tan, okay, for any angle in standard position. So again, here are those trig ratios. SOHCAHTOA, sine, cos, tan, right? SOHCAHTOA is just a way of remembering it. You technically don't have to memorize it because it is on your formula sheet, although I'm sure at this point in your math careers, you've memorized it whether you intended to or not because you use it so much, okay? So if we know a point, remember, this is all happening on the Cartesian plane, the x and y axes. So if you know a point's coordinates, its x coordinate and its y coordinates, and that point lies on the terminal arm of the angle, right? Like looking here, this point here, it does have an x value, and it does have a y value, and it's on the terminal arm of our angle. Okay, do you see how that x value and that y value can tell us about the adjacent and the opposite sides of our reference triangle, right? You can see that the y value is just the length of the side that is opposite to the reference angle, right? Look, the y, I'm going to do some coloring in here, right? Maybe I should, well, I'll use red. I usually use red for y, okay? Notice this y coordinate, whatever it is, like if this point is at, you know, y value of -4. Well, then the length of this side is just 4, right? It's a y value of -4. So opposite to our reference angle is a side with a length of 4. What about the x value? Like whatever this is here. If the coordinates of our point that is on the terminal arm of our angle, right, say it's at like 2, -4. Well, then what's the length of this side? It's 2, right? So that tells us that the adjacent side for our little reference triangle here is just the x coordinate of any point that's on our terminal arm, okay? And so the last piece of the puzzle here, we've talked about adjacent being the x coordinate, opposite to our reference angle being just the y coordinate. Well then, the last missing side of the triangle to talk about here is our hypotenuse, right? Our hypotenuse. And that hypotenuse is just going to be the distance from the origin to the point that we're talking about, the point that we know on the terminal arm of the angle, okay? And that will make the hypotenuse, and we often give it the symbol r. We call it r, you might remember from Math 20. The reason being is that it's the radius, r for radius, of the circle we would make by spinning all the way around, doing a full 360 or a full 2 pi radian, right? Notice if I take this point, go all the way around, well, now the hypotenuse of that triangle is just the radius of that circle that I just drew. Not a very good circle drawing, but that's the idea, okay? And so r is always going to be positive because it's not like it's an x value that's, on the negative x-axis or a y value that's on the, negative y-axis. R is like a combination of x's and y's, right? It's not really living in the same system as positive x's are here, negative x's are here, positive y's are here, negative y's are here. It's kind of a combination of both, right? It's a radius of a circle. So r is always by definition positive, right? But we know x and y coordinates can be negative, okay? So there's our little reference angle. Do you see where these ratios are coming from? Sine of our reference angle is going to be equal to y over r. But that's just saying opposite over hypotenuse, right? We often, for these, when we're working in standard position, we swap out adjacent and opposite and hypotenuse for x, y, and r, because remember, this is all happening on the Cartesian plane, and that can become a quicker and easier way to think about it often, right? Again, if this point has some x coordinate, right, then this point here, if we map it back, that x value there, that now tells me the adjacent side of my reference triangle relative to the reference angle, okay? This opposite side, well, it's just going to have the same value as whatever the y coordinate of that point on the terminal arm is, right? And then the hypotenuse will just be this r here, okay? So opposite over hypotenuse for our reference angle is y over r, right? Adjacent is x over hypotenuse is r. So adjacent over hypotenuse, cos, is x over r. And opposite over adjacent is y over x, right? So tan of this reference angle would be the y value over the x value, okay? So note that if you are given a point, x, y, on the terminal arm, you've already got x and y, right? If you have the point on any angle's terminal arm, you can figure out what the x and the y are for any of these ratios. R is the hypotenuse, so you can actually find that as well using your Pythagorean theorem. Just remember for the Pythagorean theorem, right? Again, for this we could say r squared is equal to x squared plus y squared. Remember for the Pythagorean theorem, it's just the hypotenuse squared is equal to the other two sides, what we call the legs. The legs are the non-hypotenuse sides of a right angle triangle, right? So those two squared equal, whoops, I don't know why I put the squared there. Sorry, that shouldn't go there. It does belong in the equation, but not on the actual triangle, obviously. The side lengths A, B, and C, right? This side squared plus this side squared equals this side squared. So take that and apply it to our reference angle. X squared plus y squared equals r squared, okay? So if you know any point on the terminal arm of an angle in standard position, think about how powerful that is. Because its x coordinate tells you the side adjacent, the y coordinate tells you the side opposite to the reference angle, and with those two, which you've already got just by knowing the point, you can automatically find the hypotenuse as well, because you can use the Pythagorean theorem with the x coordinate and the y coordinate, right? With just a quick step, you've got all three sides of the triangle just by knowing any point on the terminal arm of an angle in standard position. Let's try it out. So what we're given here is that the point P, this is just naming the point P, -5, -8 lies on the terminal arm of an angle theta in standard position. Draw the angle and the reference triangle and calculate the exact values of the primary trig ratios for theta. Well, in order to do that part, the primary trig ratios, we probably would have done this anyway, right? Draw the angle and the reference triangle. Little diagrams are your best friend in the trig unit. So let's just first think about that point. -5 is the x coordinate of the point. So I'm just going to, estimate -5, and -8 is its y coordinate, okay? And what it's telling us is that point here. So this is the point P, which is at -5, negative 8, okay, is on the terminal arm of our angle. Now notice, again, sometimes students forget that this is all happening on the Cartesian plane, right? This is just a good old point. It's where x is negative 5, y is negative 8. But for our rotation angle in standard position, we now know that that point lies on the terminal arm of our angle. So all I drew there was the terminal arm of an angle. And think about this, right? Now we know, okay, so my angle looks something like that if its terminal arm is going to pass through an x-coordinate negative 5 and a y-coordinate of negative 8. Okay, so there we go. So let's now start thinking about, right, the reference triangle we could make here if we were actually going to do some trigonometry with it, right? Again, yesterday we talked about the reference angle. We will use reference angles here as well. We don't actually need it for this one, though, because we can just start thinking, okay, well, if that is my angle, there's its terminal arm, right? Well, look, here is a side, right? How long is that side? Well, I mean, it's 8 units long, and we can even say it's negative 8, right? And here is another side. And by definition, these x and these y, they make a 90-degree angle. So we've just made a little 90-degree triangle, right? Because we know that this point, negative 5, negative 8, is on our triangle. So this side length, we can think of it as having a length of, negative 5 and an opposite of negative 8. Again, there would be our reference angle right there. And so we can use this little, reference triangle as a reference to start writing out our trigonometric ratios for this angle that is, larger than a right angle triangle could fit in it normally. Okay, so here we go. Let's try to do that. Now, you'll notice right away if we go to do sine of this angle, well, opposite over hypotenuse, we don't have the hypotenuse, right? What we call r usually in this context. But hey, we can get it, right? We can get r because we have two sides of a right angle triangle. It's always possible then with the Pythagorean theorem to get r. So let's just do that first, right? Essentially, do you see our triangle here? It looks like this. We've got this x length of, I'll call it negative 5, this y length of negative 8, right? And we can use this as a reference triangle to figure out what the ratios would be. The negatives and stuff come from the fact that we're actually working in 4 quadrants. We have x's that can be negative, right? But at the end of the day, the fundamental ideas of the trigonometry process here are the same. We've got a little right angle triangle. We can do trig with it. We can think about the ratios of the sides to one another. So let's go ahead and find r, our hypotenuse. Well, r squared is going to equal x squared plus y squared, right? Hypotenuse squared equals adjacent squared plus opposite squared. So this means we'll have that r is the square root of x is negative 5. That negative is not going to end up mattering because we're squaring it. Another reason why our r will always be positive. Okay, plus negative 8 squared. So r is the square root of 25 plus 64, which is 89. So r is just the square root of 89. I'm not going to take the square root of 89 here and get something that's less accurate, right? Root 89 is an exact value. It's not a perfect square, so if I take the square root of 89, I'm not going to get a nice number. I'm going to get an irrational number. That's going to be a decimal that I'm going to eventually have to round because it's infinite, so why bother? Why make it less accurate than an exact value of root 89? What we could do is we can't do it here, but we could maybe simplify this radical. If this had any perfect square factors, we could pull them out and just square root them, but can't do that here. So root 89 is a perfectly valid number. It's actually the best way to represent this because it's not rounded. So I'll leave it as root 89. So let's do now we can actually find the trig ratios, the primary trig ratios, sine, cos, and tan. Find ratios. All right. So the sine of our angle is going to equal opposite over hypotenuse, yes, but more and more we're going to start thinking of that as like the y over the x, right? Sorry, the y over the r, opposite over hypotenuse. In this context, we think of that as the y coordinate over the r, the radius, okay? So this will be negative 8 over an r of root 89. Okay? Now, something we should do before we move on. Do you remember we never want to have roots in our denominator, right? Because we want to do what's called rationalizing the denominator. That's just one of those things that's almost like math manners or math convention. It's just kind of considered the proper way to represent things. It holds over from a long time ago, well, maybe not that long ago, but a while ago when we were doing math without calculators and without computers, and it's incredibly difficult to divide by an irrational number. So it kind of just became the natural way that we represent them. We don't have radicals in our denominator, okay? So we always want to do what's called rationalizing the denominator. Do you remember how to do that? Well, I want to get rid of that root in the denominator, right? How can I get rid of a root? Well, I could multiply it by itself because, again, like root 2, for example, times root 2, the square root of 2 times the square root of 2 is just going to be 2, right? But by very definition, the square root of 2 is the number that when you multiply it by itself gives you 2, right? Root 4 is 2 because 2 times 2 is 4, right? So root 4 times root 4 should just be 4, and it is, because root 4 is 2, and root 4 is 2, and 2 times 2 is 4. So how do we get rid of a root 89? Well, we could multiply it by a root 89. But obviously, we can't just multiply by 1 over root 89, because that would be changing what this fraction is, right? The only thing we're allowed to multiply something by without changing what it represents is 1. So I can multiply by 1, but I can choose to represent my 1 in a, carefully chosen way, because this is just 1 now. I'm really just multiplying it by 1. So I'm not going to change what it means, but I will get rid of this radical, this irrational number in the denominator, right? The square root of 89 is a non-terminating decimal. It's irrational. So doing this will get rid of that. That's going to give me negative 8 root 89, and root 89 times root 89 is just 89. So there we go. Okay, that's the sine of this angle. We don't even know what the angle is, but we figured out what its sine ratio would have to be. Let's do the cosine of that angle now. Cosine is, adjacent over hypotenuse, but if we think of it in terms of, x, y, and r, it's going to be x over r, right? Again, the reference angle would kind of be here. Okay, so x over r, adjacent over hypotenuse. Ka toa. So x over r, we know that x is negative 5, and we know that r is root 89. Once again, I should rationalize that denominator, okay? This is technically right, but it's just the proper form is to rationalize our denominators. So same step, actually. I just need to multiply this by root 89 over root 89, because root 89 times root 89 in the denominator there is just going to become 89, which is a rational number. So this will give me negative 5 root 89 over 89. And there we go. That is the cosine ratio for that angle. Last up, tan. So the tangent of theta is TOA, right? Yes, opposite over adjacent. So opposite over adjacent, but also y over x, right? Means the same thing. So y is negative 8 over adjacent is negative 5. Y over x, whoops, I should probably write it out. Y over x, which is negative 8 over negative 5. And a negative over a negative, well, that's just going to give me a positive, right? So this is 8 over 5, positive 8 over 5. So the tangent ratio for this angle here is equivalent to positive 8 over 5. And there we go. We just drew out the reference triangle, and we use that to think about the ratios. So do you see why we call it a reference triangle, right? This triangle itself is like not really that, I mean, it is associated with this angle, obviously, but it's not like this angle's actually part of this triangle, right? A piece of the angle can be used, the reference angle, a piece of this angle can be used to think about a triangle that can allow us to think about the trigonometric ratios, right? Essentially what we're doing here is we're saying, okay, this is like a Math 30 problem. Can we turn it into a Math 10C problem and draw a little triangle that we can do SOHCAHTOA with? And since we're Math 30 students, we can recognize that really this side length is a -5 because this is happening on a Cartesian plane, and this x coordinate is at -5 and the y coordinate's at -8. But using that, Math 10 triangle to write the ratios still. Okay, so let's remind ourselves now, another little Math 20 review here. Let's talk about cast. Do you remember that saying from Math 20? Cast, right? It's just a little mnemonic that we use to quickly remember the quadrants in which each ratio is positive. But again, like anything in math, it's not just some magic trick, right? It actually makes a lot of sense when you think about where it comes from. So it's good to understand it in case you ever, forget it. We can always just come up with it by taking a second to think about it, right? So what it means, it's a little weird because it starts in quadrant 4, but otherwise it would be asked to see, which doesn't roll off the tongue as nicely. Although some people do say add sugar to coffee. If you like that one, by all means, feel free to use that. The nice thing about add sugar to coffee is that it goes quadrant 1, quadrant 2, quadrant 3, quadrant 4. But if that's not a big deal to you, I think most people probably say cast. So what that's referring to, cast, the C is letting us know that that is where cosine is positive, and all of the other ones are negative. We're going to remind ourselves of why that makes sense in a second. It's not just a magic rule, but I'm just going to run through cast really quick. A, in quadrant 1, all of the ratios are positive. So sine, cos, and tan are all positive in the first quadrant. S, you can probably guess, sine is positive in the second quadrant, while tan and cos are negative, okay? And the T in quadrant 3 is for the fact that tangent is positive there, while sine and cos are negative there, okay? So only cos is positive here, the other two are negative. All three are positive, only sine and the other two are negative. Only tan is positive and the other two are negative in quadrant 3. Now, like I said, this is not just some weird thing that we say, okay, cast, remember that, and don't forget cast. Why? Just because, right? No, it actually makes a ton of sense. Remember, sine equals y over r, opposite over hypotenuse, right? Cos is x over r, adjacent over hypotenuse. Tan is opposite over adjacent, y over x, okay? Now, where this cast comes from is just thinking about the different combinations of y, x, and r that you can get in each quadrant, right? So in quadrant 1, what's x, positive or negative? Well, this is the positive x-axis, right? This is where we would find positive x's. So x is positive. What about y? Where do we find positive y's? Yeah, up here, right? So in quadrant 1, x is positive and so is y, right? So think about it. All of the ratios then are just going to be a positive over a positive because r is always positive, right? Again, it wouldn't really make sense. Like if we say r is negative, well, what does that mean? R is not on the x-axis or perfectly a y value either, right? It's in between. It's a combination of the two, right? So it doesn't ever make sense to call r negative because r is not an x or a y, right? It's a radius of a circle. Doesn't have a sign, okay? So r is always positive. In the first quadrant, x and y are both positive. So no matter what combination you do here, you're doing a positive over a positive, right? A positive y over a positive r, that's a positive over a positive, it's positive. A positive y over a positive x, right? Opposite over adjacent. Well, opposite is a positive value, adjacent is a positive value, so positive over positive is positive. Okay, now head over here to quadrant 2 and things get a little more interesting because now we're looking with negative x's in quadrant 2, right? X's are negative over here. Okay, in fact, x's are negative everywhere over here. Okay, but y's are still positive. Y's are positive everywhere up here. So we have in the second quadrant, we have positive y's and negative x's. So think about how that's going to affect our ratios, okay? And keep in mind, we're expecting sine to come out as positive, but not cos and not tan. Let's see why. Well, if sine is opposite, right, y over hypotenuse, r, then it's still, in the second quadrant, it's still a positive over a positive, which is positive. But cos now, which is still x over r, still adjacent over hypotenuse, but our adjacent, our x, is now negative. These are the negative x's over here, right? R is always positive, so we have a negative over a positive, which is a negative. And that's why cos is going to be negative in the second quadrant. What about tan? Well, tan is opposite over adjacent. Y, which is positive, over x, which is negative. So opposite over adjacent here, y over x becomes a positive number over a negative. Positive divided by negative gives us a negative answer. And that's why we have that, all are positive here. Only sine is positive here. Because cos is going to be positive over, cos will be negative over positive, and tan will be positive over negative, giving us negative overall values for those ratios. And this logic continues all the way around through all four quadrants. Same thing different, but same logic in the third quadrant here, where now, if we think about it, what's down here for y's? These are all negative y's, right? And now we've got negative y's, and we've also got our negative x's with the overlap there in the third quadrant. So in the third quadrant, we're dealing with the negative x's and negative y's. So if we think about sine, opposite over hypotenuse, or y over r, well, y is negative, r is always positive. So sine is going to be negative. It's a negative over a positive, y over r. Okay, cos is going to be negative. X is negative. So adjacent over hypotenuse, x over r, is a negative number over a positive number, giving us a negative result. Tan is y over x, opposite over adjacent. So we've got negative y divided by negative x. Negative over negative gives us a positive. And that's why in our cast rule, only tan is positive in the third quadrant. Because a negative over a negative, a y over an x, will give us a positive when both y and x are negative, like they are in the third quadrant. And you can see where this is headed, right? For the fourth quadrant, where only cosine is positive, well, look, x is positive again in the fourth quadrant, right? These are all our positive x's on this side of the y-axis. So we've got positive x's in the fourth quadrant, but we're down here, we have negative y's. So adjacent over hypotenuse, r is always positive. We've always got a positive hypotenuse here. So positive x over positive r gives us a positive cosine ratio. Negative y over positive r gives us a negative sine ratio. And a negative y over a positive x gives us a negative tan ratio. So look, only cos is positive, the other two are negative, right? And that's where this cast rule comes from. So truth be told, we usually do just kind of reference cast because we can't, draw these all out every single time and think about them. But it's important to understand them because, as always in math, it's better to understand than to memorize. And when you memorize, if you forget, you're out of luck, right? If you understand, you can always just take a couple seconds to think about it and say, oh, okay, I'm in the fourth quadrant, so cos would be positive here. Or my tan ratio that I'm working with should be negative because I'm in the fourth quadrant. All right, let's try out an example reminding ourselves of cast. So it wants us to state whether the following will be positive or negative. Cosine of 30 degrees. Well, we can use cast here, right? We can just say, okay, C-A-S-T. Which quadrant is 30 degrees in? Well, if this is 0, this is 90, right? Starting from 0, rotating that way, we're not even to 90, so we're in quadrant 1, so we can kind of predict it'll be positive, right? We're in quadrant 1. They are all positive in quadrant 1, so it will be positive. Cosine of 30 degrees will be greater than 0, okay? But again, just to remind ourselves of why this makes sense, this is a positive x value, right? And this is a positive y value, and this is a positive r, and r is always positive. So positive x over a positive r, positive over positive, cosine overall, which is just a ratio. Remember, cos of 30 is just a ratio. It's a fraction. It's a number. It'll be a positive number here. It's the ratio of this side to this side, right? And in this case, that will be a positive ratio. Okay, ready for some radians? 5 pi over 4. Okay, let's think about what quadrant we're in. So reminder, we've got our 0, or 2 pi if you go all the way around. Then we get 90, which is pi over 2. Okay, it's 180 is pi. Again, if you can remember that 2 pi radians is a full circle, it becomes pretty quick after that because you can say, all right, pi would be halfway to 2 pi. Quarter of the way to 2 pi would be pi over 2, and 3/4 would be 3 pi over 2. So we've got to ask ourselves, where does 5 pi over 4 land? And I always like to do with these, like my kind of reference point at first is I say, all right, is that more than pi or less than pi, right? More than 1 or less than 1 pi? Well, think about it. 5/4, right? I mean, imagine a pizza. There's 4/4 of a pizza. There's 5/4 of a pizza, right? Is that more than 1 pizza or less than 1 pizza? Well, it's more, right? So we've gone past a pi, past a full pi. By how much? By 1/4 of a pi, right? So past pi and then another quarter pi. So something like that. Okay, we're not quite to 3 pi over 2, right? It often helps, like if you're really stuck on it, you can say, well, pi, that's just 4 over 4 pi. We've obviously gone past that. What would 3 pi over 2 be? Well, multiply by 2 over 2 to get a common denominator. You can see that this would be 6 pi over 4, right? So we're not quite that far. We're only at 5 pi over 4. So in fact, we can actually work out that we're exactly halfway between pi and 3 pi over 2. This would have a 45-degree reference angle or a pi over 4 reference angle if we were worried about reference angles here. All right, and that's honestly all we need to know. We're in the third quadrant. So looking at our cast here and thinking about it, in the third quadrant, tan, didn't mean to erase that. Tan is the only one that's positive, right? So sine is negative. So this will be negative. So negative, right? And again, it's negative because we want, right, sine of 5 pi over 4 is going to be negative, and sine is y over r. Well, r is always positive, and this y value of our reference triangle is a negative number, right? These are the negative y values down here. So it makes sense, okay? Let's do tan of 5 pi over 3. So I want you to try this on your own. Maybe pause the video. Try thinking about drawing out 5 pi over 3. Ask yourself, is this more than a full pi, less than a full pi? How does it compare to like 2 pi? And that lets you roughly place it in the 4 quadrants. Okay, so we're going to be past pi here for sure, right? Past 180. Because 1 pi would be 3 over 3. Right? 3 over 3 pi would be this far. Well, we've gone to 5 over 3. So we've gone 2/3 further. In fact, think about this, right? What would be 2 pi? What would 2 pi be? It would be, as a fraction over 3, that is, it would be 6 pi over 3, right? That would be 2 pi. So we've only stopped pi over 3 short of a full 2 pi. Right? 3 pi over 2, if you want to express that as a fraction over 3, multiply, I guess you'd have to get a common denominator there, wouldn't you? 3 pi over 2, I mean, we could meet at 6, so this would be like 9 pi over 6, and this would be, multiply by 2 over 2, 10 pi over 6. So we've gone past this 3 pi over 2, right? We can see that we are, like I said, our reference angle is in our terminal arm is in quadrant 4. We can work out that our reference angle must just be pi over 3, right? 2 pi would be 6 pi over 3. We did 5 pi over 3, meaning that there was 1 more pi over 3 to go to get all the way to 2 pi. Okay, so there's our angle. But we're just concerned now with, is that positive or negative? That's all this question actually wants us to answer. So in quadrant 4, only cos is positive. Well, we don't have cos of 5 pi over 3 here. We have tan of 5 pi over 3. So what's it going to be? It's going to be negative. Tan of 5 pi over 3 will be negative. Okay, and cast is all we really need, but again, always good to understand where it comes from. Why is tan negative in quadrant 4? Well, whatever this y value is, that's a negative y, right? And what about this x value? That's a positive x, right? right? So opposite over adjacent, y over x is a negative over a positive, giving us a negative tan. All right. Something new now, something that is not Math 20 review. Let's look at the reciprocal trig ratios. So, don't forget, right, what we're talking about with sine, cos, and tan is nothing more than a ratio, right, a number. It's the ratio of one of the sides of a right angle triangle to another side, right? Again, like if this is our angle and this is 3 and this is 4 and this is 5, then each of the sine, cos, and tan is just one of those, well, two of those in ratio to each other, right? Sine of theta for this triangle would be 3 over 5. That's what it's equivalent to. Notice it's just a number, 3 over 5 or 0.6, okay? It's just a ratio. What sine does is compare the opposite side to an angle to the hypotenuse of the triangle that angle would be a part of, right? And again, the reason, like these ratios, they hold for all similar triangles. So for example, this triangle here, it might be bigger in terms of individual side length, like this might be 6 and this might be 10, but the ratios still hold. And that's why we just say the sine of the angle will always be the same ratio. When we say like sine of 30 degrees equals something, that's because any right angle triangle with a 30-degree angle here, even though the side lengths individually might be different, right? 3 is different than 6. The ratio of this side to the hypotenuse will be equivalent if that angle is equivalent. So look at this one, right? 3 over 5 is the same ratio as 6 over 10. 3 over 5 equals 6 over 10. This is just like a reduced version of it. So I just wanted to remind you, because sometimes students forget that all sine, cos, and tan are ratios. Now, there's no reason we couldn't also think about the ratio of hypotenuse to opposite, right? We often think of sine, opposite over hypotenuse, but what's wrong with thinking about the ratio of hypotenuse over opposite? And that's all the reciprocal trig ratios are. It's rethinking, well, maybe not even rethinking, it's just looking at a different ratio. So each primary trigonometric ratio, sine, cos, and tan, has what we call a reciprocal ratio. And it's a good name because that's all it really is. It's the reciprocal of sine, of cos, or of tan. Remember, the reciprocal of a number or an expression A is just the flipped version, right? The reciprocal of A would be 1 over A, thinking about A as being A over 1 there, right? The reciprocal of any fraction or ratio, A over B, is just B over A. And so the reciprocal ratios are just, well, instead of opposite over hypotenuse, hypotenuse over opposite. Instead of adjacent over hypotenuse, hypotenuse over adjacent. You get the idea, right? So we can express them using our x and y coordinates as well as r. We'll do that in a second, but let's just introduce them. Now they have their own names, and sometimes students don't like the names at first. I remember thinking, why do they have to call it that? Okay, it has to do with the definitions and where they originally come from and all that, but I get it. It is a little annoying. So the reciprocal ratio of sine is what we call cosecant. Now, I know, like I said, that's a little annoying because it starts with cos, and you think, come on, shouldn't that go with cosine? Okay, again, it goes into some of the origins and derivations of the names of these things that we won't get into, but just keep that in mind. The reciprocal of sine is what we call cosecant, or CSC for short, right? The same way we write SIN as short for sine, we write CSC being short for cosecant. So the cosecant of any angle is just 1 over sine, or instead of opposite over hypotenuse, it's hypotenuse over opposite, right? Again, there's no reason we couldn't think for this angle, what would be the ratio of any triangle that angle's a part of, hypotenuse to opposite, right? We could say 10 over 6, or 10 over 6 or 5 over 3. Those are equivalent ratios, right? And that would be the cosecant of theta for that example I've made up there. It would be hypotenuse over opposite, because sine is opposite over hypotenuse, so the reciprocal, cosecant, is hypotenuse over opposite. The reciprocal of cosine is what we just call secant, or SEC for short. So just like cosecant is hypotenuse over opposite because it's the reciprocal of sine, secant is hypotenuse over adjacent because it's the reciprocal of secant. And you can probably guess the reciprocal of tangent is going to be adjacent over opposite. And we give it the name cotangent, or COT for short. okay? But like all the other trig ratios, these are just trig ratios. It's just that there are the reciprocal versions of the ones you already know and love, okay? So cosecant is the reciprocal of sine, secant, reciprocal of cosine, and cotangent, reciprocal of tangent. Okay, let's try thinking about these in terms of x, y, and r, which again is really very similar to adjacent, opposite, and hypotenuse, but thinking about them in terms of like on a Cartesian plane with an x and a y axes and, you know, a little deeper in standard position and all that. So what would cosecant of theta be? So first thing I'll ask you, what is cosecant the reciprocal of? It's the reciprocal of sine, right? I know that's a little confusing at first because it sounds like it should be cos because of cosecant, but cosecant goes with sine. So this is going to be hypotenuse over opposite, right? I mean, sine theta is y over r. That's opposite over hypotenuse. So what will cosecant theta be? It'll be r over y, right? Hypotenuse over y. Here, let's just draw a little reference triangle to think about. Okay, we got our y, our x, and our r, opposite, adjacent, hypotenuse. Okay, so cosecant theta is r over y. Secant theta is the reciprocal of cos. So cos is x over r, adjacent over hypotenuse. So secant is going to be r over x, hypotenuse over adjacent. Okay, and cotan theta, well, tan theta is opposite over adjacent, y over x. So cotan theta is the reciprocal of that. It is x over y. And that's really all there is to the reciprocal ratios, right? Now, your calculator does not have the reciprocal ratios. You'll look in your calculator, there is no there is no cosecant, secant, or cotan. There's just sine, cos, and tan. So while we can work with these reciprocal ratios and they're great and all that, often what we're going to end up doing when it's time to, like, if we actually need to calculate something, that being said, a lot of the times in this unit, we can just get exact values without ever even touching the calculator, okay? But you will need to, like, if you need to put something in the calculator or something like that, you will need to flip it to a sine, a cos, or a tan first, but that's easy to do, right? If you're given cosecant, we'll just flip it, and now you've got sine. Okay, let's try some examples. All right, so first one, the point D, which is at -512, lies on the terminal arm of an angle theta in standard position. Remember, knowing a point on the terminal arm is huge. We can figure out x, y, and r pretty much automatically. So let's think about where would, well, -5 is here. And this isn't to scale, obviously, but, you know, 12 is positive. It's somewhere up there. So I say it's not to scale because I made -5 look as big as 12, but we just need to get a rough bearing here so that we can kind of think about our angle, think about what quadrant it is in, and think about a reference triangle and eventually the ratios for part B there. Okay, so sketch and label a diagram with the side lengths. We can see our angle, the theta itself looks something like that, right? Our reference angle would be this here, and we've got our opposite, our y, okay, we know it's 12. We've got our r, and we've got our x that we now know is what? How big is x? Yeah, it's 5 units long, and it's the x value itself is -5, okay? So it wants us to sketch a diagram and label with the side lengths. 2 out of 3 already done just by knowing the coordinates of a point on the terminal arm. R, how can we get it? Well, if we were back in, you know, Math 9, and I said, hey, what is this side, right? You'd be able to find it even back in Math 9 with the Pythagorean theorem. So it's the same thing. We're just applying it in a bigger picture context here now, okay? So Pythagorean theorem, the hypotenuse squared, r squared, will equal the 2 legs squared and added. So -5 squared plus 12 squared. So r squared is going to be -5 squared is 25. 12 squared is 144. So r squared is 169. And then square root both sides, because we don't want r squared. Remember, that's a common student mistake, forgetting to square root. So square root both sides. And the square root of 169 is 13. If you're saying, shouldn't it be plus or minus? That's technically true, but remember r is never negative, right? R is by definition positive because it's not like it has an x coordinate or a y coordinate. It's just r, right? It's at an angle somewhere. So r is just 13. So there we go. Now we can label our r on our reference triangle. This triangle has a hypotenuse of 13. Okay, now it wants us to write the three primary trig ratios for theta and the reciprocal ratios. Okay, so here's our first example where we're taking the reciprocal ratios for a spin. Let's just quickly redraw our reference triangle so we can think about it as we go. It's opposite, its y is 12, it's adjacent, its x is -5, and now we know that r, its hypotenuse, is 13. Okay, so thinking about this kind of reference angle there, so sine of our angle theta is going to be y over r, right? Y is 12, r is 13. Opposite over hypotenuse. Done. What's cos of theta? Well, cos is adjacent, x, over hypotenuse, r, right? So cos of theta will be -5 over 13. Okay, x over r. And again, we can double check with our cast, or even what some students like to do is just leave the negatives out of this and then use cast to tell you what the ratio would be. So like just make this 5 and say, okay, it's adjacent over hypotenuse, but I know that this angle is really in quadrant 2 and cos should be negative in quadrant 2. Sine would be positive. Okay, tan of theta would be opposite over adjacent, so y over x, right? Opposite over adjacent. So opposite is 12, adjacent is -5. So -12 over 5, or 12 over -5, means the same thing. All right, what about the three reciprocal ratios? I mean, once you've written the three primary, the reciprocal are pretty quick and easy because you just got to flip them. So if sine is 12 over 3, then cosecant, that's the reciprocal of sine, is going to be 13 over 12, right? R over y instead of y over r. What goes with cosine? Do you remember the name of the reciprocal ratio for cosine? It is secant, right? SEC. So secant of our angle theta is going to be, well, cosine was -5 over 13, so secant is going to be -13 over 5, right? So, or if you like, 13 over -5. Means the same thing. Maybe I'll write it that way. Okay, cotangent, what's that going to be? Well, if tan was 12 over -5, then cotan is going to be -5 over 12. X over y instead of y over x. Okay, and there we go. We wrote the three primary trig ratios and their reciprocal ratios. They're just comparisons of two sides of the triangle, right? The ratios of two sides of the triangle. Okay, the reciprocal ones just flip the ones we're used to from previous courses, but they're still just ratios. All right, now here's kind of an interesting one. If cotan of theta is equal to -2 over 3, determine the exact value of sine theta and secant theta for 3 pi, for this domain, right? For 3 pi over 2 being less than or equal to theta, being less than or equal to 2 pi. Okay, so this is good because technically cotan will be negative in two quadrants, right? We know from cast that cotan is negative in quadrants 2 and 4, right? Again, wherever tan is negative, cotan's going to be negative because all we're doing is taking the reciprocal. That's not going to change their signs, right? Notice here, where sine was positive, cosecant was positive. Where cos was negative, secant was negative. Where tan was negative, cotan was negative, right? Taking the reciprocal isn't going to change it. So cast applies to all the reciprocal ratios as well. So there are two places where tan would be negative. So this would technically, we would have to give 2 answers for sine and 2 answers for secant, one each in quadrants 2 and quadrants 4. However, they've limited our domain here. So we're between 3 pi over 2 and 2 pi. Well, where is that? Let's think. This is 0 or 2 pi. This is pi is 180, right? So this is halfway, pi over 2. And then this is going to be, well, it's halfway to 2 pi from pi, right? So right here is halfway between pi and 2 pi. That's 1.5 pi, or 3 over 2 pi, okay? So we are between 3 pi over 2 and 2 pi, meaning that we are in just this quadrant. They're limiting our domain to just quadrant 4, okay, between 3 pi over 2 and 2 pi. Now, it's telling us that cotan of theta is negative 2 over 3. So let's think first about what that means. What is cotan? Well, it's adjacent over opposite, right? Meaning that it is x over y, as opposed to tan, which is y over x, okay? So think about that. That means that the ratio of x to y is negative 2/3. Combine that with the fact that we know we're in quadrant 4, we can work out that, okay, x must just be 2 and y is negative 3, right? That would give us a ratio 2 over negative 3, which is equivalent to negative 2/3, negative 2 over 3. So now that's pretty powerful because now we know that, all right, 2, right? And negative 3 kind of gives us a point on the terminal arm of this angle. So we can start thinking about what our angle is, right? It goes like this. We actually don't need to know what the angle is, but we can still kind of think about it and visualize it, right? And what we need to figure out, I'm just going to draw our reference triangle a bit bigger so we can see the relationships a bit better. That's a 2, that's a negative 3. Okay, just took this and kind of copied and pasted it bigger. Okay, we are asked to figure out sine theta. Well, sine is opposite over hypotenuse, or y over r, right? And then we're asked to find secant. What is secant the reciprocal of? Secant is the reciprocal of cosine, right? So cosine is x over r, so secant is going to be r over x. Okay, so we've just got to figure out, what are we missing to be able to write actually both of these ratios? We're only missing one thing. Do you see it? Yeah, we just need to know what r is, and we could say what the value of sine theta is and the value of secant theta is. How are we going to get r? Well, we're back in grade 9, right? We just need to do Pythagorean theorem. So let's just say step 1, find r, because we need r for writing both the sine ratio and the secant ratio. So r squared here is going to equal 2 squared plus negative 3 squared. A squared plus b squared equals c squared. Okay, so then r squared is 2 squared is 4 plus negative 3 squared is 9. So r squared is 13, and therefore r is the square root of 13. Again, not going to round it. Why get a rounded, or what? Not going to actually do root 13 on my calculator and get a less accurate rounded irrational number. Nothing wrong with root 13. That's a perfectly valid expression. In fact, it's a exact value. Okay, so now we just need to write our ratios. So step 2, find sine theta and secant theta, which is just a matter of putting the right sides of our reference triangle in the right spot in those relationships. So sine is y over r. So sine theta will be, well, y is negative 3 over r, we now know is root 13. Anything I should do there? Should I leave it like that? Right, I should always rationalize my denominator, right? That's just considered like good math etiquette. So I'll do root 13 over root 13 to get rid of that irrational number that's in my denominator technically. So I'm going to have negative 3 root 13 over 13 when I do that. Okay, let's do secant theta. But again, we know that secant theta is just hypotenuse over adjacent. It's the reciprocal of cosine, right? So cos is adjacent over hypotenuse, or x over r. Therefore, secant is hypotenuse over adjacent, or r over x. So now that we know r is root 13, we've got root 13 over x, which is positive 2, No need to rationalize my denominator here because my denominator is just 2, right? My irrational number's up in my numerator, and that's totally okay. So this is sine theta, and that was secant theta. Okay, so what we do there? Again, we use the fact that cotan theta was negative 2/3, and we were in the 4th quadrant to figure out, all right, well, what would the other ratios be, right? We can find the third side of the triangle, and then it's just a matter of relating the sides to each other correctly with our trigonometric ratios. Okay, so we're going to start building up something here, okay? And we'll start out with the basic idea of what this unit circle is, okay? It is very, very powerful. It's an amazing tool to have in our pocket. I don't know if it's so much a tool, but like a set of relationships, I guess is what you could call it, okay? Now, the unit circle, oftentimes like people are told to memorize it. You don't need to memorize it. You need to know everything that's on it. I'll say that right off the bat. But if you can understand a few key relationships and some things going on, that's all you really need to know, and you can kind of build the whole unit circle yourself. So I'm going to give you a little preview of where we're headed, okay? It's going to look a little scary. You do need to know everything on this circle, okay? But you absolutely should not, I'm saying it right off the bat, I do not recommend, I'm a math teacher. I don't have this memorized, okay? What I've done is I've thought about a few, I know and I understand a few key relationships, and I can figure out anything on this circle by using and applying those relationships. I can figure out anything I need on this circle, okay? So we're going to start out, before we build up to that, okay? What is a unit circle? It's actually pretty straightforward. It's a circle with a radius of 1. And its center is located at 0, 0. We call this a unit circle. In math, unit often means 1. A unit means it's equivalent to 1. Okay, now, got it? Did you imagine that? You don't have to imagine it. Here's a picture of it, but okay, got it? It's a circle with a radius of 1 centered on 0, 0. You can see how this is applicable to trigonometry, right? You can imagine rotating around this unit circle. R would be 1, right? R, the radius is 1. X, Y, triangles, fun stuff, okay? Now, consider a point P that lies anywhere on the circumference of the circle. This point has the coordinates X, Y, okay? So again, maybe the point is here, right? You could also imagine a point over here. Whoops. You could just as easily imagine that the point is over here, right? It has coordinates X, Y. X is negative in that case, and Y is also negative in that case, right? Any point along the unit circle. But something important to remember, any point on the unit circle is going to have, when we think about a reference triangle, that R will be 1, okay? All right, now it wants us to use the Pythagorean theorem to create an equation for this circle. So the equation of a circle, if you want to graph a circle, like you can try it now on your graphing calculator, if you want to graph a circle, well, think about it. It comes from the Pythagorean theorem because look, X, Y, and R, well, we could just say X squared. Using the Pythagorean theorem, we could say that the X coordinate plus the Y coordinate squared will equal R squared. And for a unit circle with a radius of 1, that just means X squared plus Y squared equals 1 squared. And therefore, X squared plus Y squared equals 1, right? Because 1 squared is just 1. Just going to move this over. I didn't leave myself much room here. Okay, shouldn't be working sideways, but forgive me, there's no space to work downwards. Okay, now, as an equation that we could graph, right, we'd want to isolate Y. So this means that subtracting X squared from both sides, we get Y squared equals 1 minus X squared. And square root both sides, you get that Y equals the square root of 1 minus X squared, plus or minus, right? Because again, when we take the square root, we've got to consider the fact that 1 minus X squared squared would give us Y, but so would negative 1 minus X squared. If we squared that, we would get Y, right? And if you put in your calculator, if you go and you put in Y1 equals square root 1 minus X squared, what you will get is a semicircle with a radius of 1. If you then put in negative root 1 minus X squared, you'll get the other half of the circle. Okay, and you can do this. I mean, what would be the equation for a circle with a radius of 2? You can probably guess it would be, starting from x squared plus y squared equals 2 squared, right? X, y is the coordinate of any point on this circle. Whoops, I drew y in a weird place. Y should be up here, of course, okay? And therefore, y is going to be plus or minus the square root of 4 minus x squared, right? So we can actually draw any circle, okay, or the equation of any circle by using the Pythagorean theorem. We're often more interested in this unit circle just because it's super handy, and you'll see why. In fact, we're about to see why. It's because of this fact. The unit circle has a radius of 1, which makes it a really great way to easily think about our trig ratios, especially sine and cos, okay? Because think about this. If r equals 1, then sine theta, which is just opposite over hypotenuse, or y over r, on the unit circle, it's just going to be y over, well, r is 1. So sine theta will just be y, meaning that whatever this y coordinate is, we know that it is the sine of this angle, right? Whatever that y coordinate is the sine of this angle. And this holds for any point if that point is on the unit circle, because the radius, r, the hypotenuse of our triangle, is 1, right? So what is the sine of this angle? Sorry, my cat's meowing in the background. What is the sine of that angle that I just drew? Well, it would be y over r. Y over 1, it would be y, right? Whatever the y coordinate of this point is the sine of that angle, okay? Because r is just 1 and sine is y over r. Similarly, for cos theta, on the unit circle, well, always it's x over r, but on the unit circle, that becomes, well, r is 1. So the cosine of any angle where it intersects with the unit circle just becomes the x coordinate of that point where the terminal arm meets the unit circle. Do you see the logic there, right? So what is the cosine of this angle here? Well, it's just the x coordinate of this point, because that point is on the unit circle, and that's where the unit circle intersects with the terminal arm of that angle. So if we do x over r, we're just doing x over 1. So if we know any point on the unit circle, since the r, the hypotenuse, is going to be 1, then we know that the x value is the cosine of the angle whose terminal arm passes through that point on the unit circle, right? It's pretty powerful, right? A powerful tool. Like, again, whatever this point is here, let me just clear this up a bit. I've added a lot of stuff. Whatever this point is here, it's a point, so it has an x and a y coordinate, but it's a point on the unit circle. And so if we picture an angle that goes through that point, or whose terminal arm goes through that point, well, this hypotenuse here is 1. And so for whatever this angle is, right, what is the cosine of that angle? Well, I can figure that out just by looking at the x coordinate of this point, because x over r is just x over 1, or x, right? And sine, which is y over r, is just y over 1 because the hypotenuse is 1. So the y coordinate of this point on the unit circle will be the sine of that angle. Pretty powerful stuff, right? Because now that we know that cos theta is x and sine theta is y for any point on the unit circle intersecting with the terminal arm of an angle, we can think of any point on the unit circle as p cos theta, sine theta. The x coordinate, it will just be cos theta. The y coordinate will just be sine theta. And you might be saying, okay, that's great if we're on the unit circle, but what if we're not on the unit circle? What if the point is not found on the unit circle? Well, we can always, even if our final answer isn't like the actual unit circle values, we can always think of the unit circle ratios even when our radius isn't 1. Because remember, the ratios hold for all similar triangles, right? Like we talked about earlier. You could do a 3, 4, 5. And yes, this triangle might be individually, each side is twice as big, but all of the ratios are the same, right? The ratio of 3 to 4 is the same as the ratio of 6 to 8, for example, right? This triangle is just in there. So that angle, okay, its ratios, its sine, its cos, its tan, and its cosecant, secant, and cotangent for that matter, are still the same because the ratios are still the same, okay? They're similar triangles. So even when the radius isn't 1, we can still refer back to those unit circle ratios because we just get similar triangles, right? Which still have the same shape and the same reference angle and therefore the same ratios of side lengths, even if the side lengths themselves individually are different, right? Looking at this diagram here hopefully kind of gives the idea. Even though the radii of the red and the blue circles formed by the terminal arm below are different, the ratios of each side in the corresponding reference triangles are still the same, right? This blue circle clearly has a different radius than this red circle. So if this red circle were, say, a unit circle, if this had a radius of 1, and maybe this has a radius of 2, right? That's okay because the triangles and the ratios involved are the same for both, right? So we can still think about the unit circle and the nice fact that on the unit circle, sine theta is the y coordinate and cos theta is the x coordinate, even if we're not actually on the unit circle. Okay. Now, again, sometimes we'll have to think a little deeper and convert it back, but at least that ratio piece can be handy in many situations, even when r is not necessarily 1. Okay, let's try some examples out using this fact, using the unit circle where r is 1, and therefore sine theta, y over r, is just y over 1, or y, and cos theta, x over r, is just x over 1, or x, right? So that cos theta is just the x coordinate of a point on the unit circle, and sine theta is just the y coordinate of a point on the unit circle, as long as that point is where, well, if theta, the terminal arm, goes through that point on the unit circle. Let's try it out. All right, so a point 0.342, 0.940 lies at the intersection of the terminal arm of an angle in standard position and the unit circle. All right, that is great because now we know this is cos theta, this is sine theta. Okay, whatever our angle is, this is the cosine of that angle, and this is the sine of that angle. Guaranteed, because if it's on the unit circle, r is 1. So x over r is just x, y over r is just y. Okay, if that point is on the unit circle, then that's the cosine of the, well, if that point intersects the terminal arm of the angle and it's on the unit circle, this must be the cosine of the angle, this must be the sine of the angle. We want to use the x coordinate. We could use both. This question's just telling us you got to use the x coordinate just for, I don't know, they felt like telling us we had to determine the measure of theta. If 0 is less than or equal to theta, which is less than or equal to 360, or I guess less than 360, it says, round your answer to the nearest degree. All right, here we go. Let's draw a quick sketch just to think about it. Like I said, in the trig unit, a quick sketch is your best friend, okay? So let's just think about this. Here's our unit circle, which we know has a radius of 1, okay? Now, our angle, it's telling us that where our angle's terminal arm intersects the unit circle is at the point 0.342, 0.940. So which quadrant are we in? Right, we're in quadrant 1 because x is positive and so is y, right? So we must be up here. Okay, so let me just draw what a terminal arm in quadrant 1 would look like. Something like that. Okay, and here's the magic, well, I shouldn't call it magic, the math coolness, okay, of the unit circle. Look, this point here is the point of intersection of the terminal arm of our angle. We're trying to figure out what that angle is, right? That's what we're trying to figure out. What is this angle? Okay, but we know that that point that point is at 0.342, 0.940. So the x coordinate of that point is 0.342. The y coordinate of that point, things are getting a little crowded here, is 0.940, right? That's where that point is located. And since it's on the unit circle, what's this distance here? Notice how this is just the radius of the circle, so this is just 1 because we're on the unit circle. And so what is cos of theta? Always, well, cos of theta is x over r. But r is 1. So on the unit circle, well, if our angle's terminal arm intersects with a point that we know on the unit circle, then cos theta will just be the x coordinate of that point because it's x over 1, right? So cos of theta is the x coordinate of this point, which is 0.342. So cos theta is 0.342. Now we want to figure out what the angle is. So how do we do that? Well, little reminder, right now we have the cos of theta. We need to solve for theta, right? So it's algebra. We need to do the inverse operation of cosine, right? Again, x plus 2 equals 4. How do you solve for x? Well, right now we're adding 2. The inverse operation, meaning the operation that undoes adding, is subtracting. So subtract 2 from both sides. X is 2, right? 3x equals 12. The inverse operation of multiplication is division. X is being multiplied by 3, so to undo that, we do the inverse. We divide. So x is 4, right? And we could do tons of them. Squaring, the inverse operation is square rooting. So the inverse operation, what we need to do to undo the fact that we're taking the cos of theta, it's got a very creative name. We call it inverse cos, right? On your calculator, that's second cos or shift cos, okay? Now, I haven't really mentioned it much yet. You're probably used to in your trigonometry units that you always make sure your calculator's in degrees, right? If you're taking any like physics courses, we always tell you make sure your calculator's in degrees. Well, now that we work with radians, we've got to be a little more on our toes about that. We might sometimes need to be in radians. We might sometimes need to be in degrees. Typically, we work with what the question used, right? So since this question used degrees, we can use degrees here, or we will use degrees here, right? Makes the most sense to give our answer in the same form they referenced, the same unit they referenced. But I just want to mention here, okay, you will be switching now that you're in Math 30 back and forth between radians and degrees. For this one, we want to be in degrees. Let me show you quickly a reminder of how to change the mode for your calculator. So we are going to start out by going to mode. It should be just to the right of your second button, okay? So you go to mode there, and then it's the fourth row. You see where it's in radians or degrees. So for the question we're on right now, we're going to want degrees, okay? But you will encounter situations where you want radians. So just, keep in mind, don't be a robot. You can think, does my answer make sense, right? Like if you get something like 0.3 degrees, that's a little bit weird. It's not impossible, but it's worth it to say, hang on, that number would make more sense as a radian than a degree. Okay, so once again, I'll show you that. It was mode, and it is degrees that we want. So we would go to degrees, hit enter to select it, and then you can just hit clear or second quit to get out of that menu. Okay, all right. So we want degrees. Since we got the calculator open, let's just put that in. So we wanted to take the inverse cos of both sides. So we wanted to take the inverse cos of 0.342. Let's remind ourselves of how to do that on the calculator. We would want to go second cosine of 0.342, right? Do you see how above cos on the cos button, there's that little cos to the -1? That's inverse cos, right? So that's why we press second to bring up inverse cos. And it looks like it's 70 degrees, okay? So 70 degrees is theta. Theta is 70 degrees. Now, if this were, what we do need to do is kind of think about, all right, which quadrant are we in? because, again, when doing this inverse cos stuff, we would never use a negative. Okay, this is technically all reference triangle stuff, not actual full in 360 stuff. But we are in quadrant 1, so that is actually just our angle. Our angle is just 70 degrees. Okay, so there we go. We're in quadrant 1 at 70. We could have also used sine, by the way. I know it told us to use the x coordinate, but we could have just easily said sine theta is y over r. If we're on the unit circle, then r is just 1. So sine theta is just y. Therefore, sine theta is 0.940. So what's theta? It would be the inverse sine of 0.940, which gives you also 70 degrees. Okay, test it out for yourself, right? So you can see, okay, we've just figured out based only on the fact that this point is on the unit circle, okay, and therefore part of this reference triangle where the hypotenuse is 1, well then the x-coordinate must just be cos theta, and the y-coordinate of that point must just be sine theta, because that point is on our terminal arm and it's on the unit circle. Pretty cool, huh? All right, now we know the point x, 5/13, is on the unit circle in quadrant 2. Determine the x-coordinate of the point. Well, what do I always say, right? Let's draw a little picture. Might help us recognize some relationships here. So, first thing, it's in quadrant 2, okay? Because again, 5/13 our point could be in quadrant 1 or 2, because all we know is that y is positive 5/13. Okay, so it could have been, somewhere here or somewhere here, but the fact that it's in quadrant 2 means we're dealing with something over here. We're expecting a negative x when all is said and done. Okay, now it's on the unit circle. So I'm just going to draw our point. Let's just think about our point. That is the point x. We're trying to figure out what x has to be. 5/13 is the y-coordinate, right? Meaning that this is 5/13. Okay. But what do we know? We know that for the unit circle, centered at 0, 0, the radius is 1. So whatever x is, we can think of it as this side of the triangle, and y is 5/13. So transport yourself back through space and time to grade 9, and you'll realize, hey, we were doing this stuff in grade 9, right? A lot of this trig stuff, it's just the setup that really is math 30. And then most of the calculations are like grade 9, grade 10 trigonometry, right? It's about basically, I think of grade 12 and grade 11 trig as like, turn it into a math 10 problem, right? Think about a way to look at it as like a math 10, math 9 problem. And from there, you just use your basic triangle relationships. So here we go. How would you find this side of the triangle? Now be careful, it's not 1 squared plus 5/13 squared, right? Remember, when doing the Pythagorean theorem, when we do a squared plus b squared equals c squared, this has to be the hypotenuse. These two, you can switch them around because we're just adding them anyway, and the order you add doesn't matter. So these are just the two legs of the triangle, the non-hypotenuse sides, but the isolated one must be the hypotenuse. So that means what we've got here is that x squared plus y squared, 5/13 squared, needs to equal r squared, 1 squared. Right? Meaning that x squared, I'm just going to drop the color coding here now, x squared plus, 5/13 squared, that's 5 squared over 13 squared. 5 squared is 25, 13 squared is 169, and 1 squared is 1. And we're getting there. We just got to solve for x now. So x equals, let's subtract 25 over 169 from both sides. And let's get a common, whoops, sorry, I forgot that x was being squared. Let's get a common denominator here so that we can combine those two, terms on the right side. So 1 is 169 over 169 minus 25 over 169. And then that means x squared is 169 minus 25 is 144 over 169. And finally, square root both sides. We get that. Ooh, I really didn't give myself enough room here. We get that x is just the square root of 144 over 169. And hey, those are actually both perfect squares, so this worked out nicely. The square root of 144, 12. The square root of 169, 13. Now, we took that square root, so we got to keep in mind, could be plus or minus, right? 12 over 13 squared would be 144 over 169, okay? But so would negative 12 over 13 squared. However, there is one that's correct here, okay? And it just comes down to the fact that we are in quadrant 2. So should x be 12 over 13 or should x be negative 12 over 13? Right, it's negative. In quadrant 2, x's are negative, right? If this had said in quadrant 1, that would be perfectly valid. The negative would be wrong and the positive would be right if this had said quadrant 1, okay? But it didn't. We're in quadrant 2, so y is positive like we'd expect, but x should be negative. So x is, since we're in quadrant 2, so x is negative 12 over 13. So the coordinates of this point that intersects with the unit circle must be negative 12 over 13, 5 over 13. If you wanted, you could check your work by using the Pythagorean theorem to make sure you get a radius of 1, and therefore that this really is on the unit circle. That actually leads nicely into what we're going to do in the next example. All right, so this one asks us, is this point, root 5 over 5, to root 5 over 5, is that point, does it lie on the unit circle? Let's just think about what that's saying, right? Because if it is, then it's a point on a circle that's centered at 0, 0 with a radius of 1, right? That's, if it's on the unit circle, that's where it's got to be. So let's just quickly draw that out and think about it. Because we can see we're in the first quadrant again because x is positive and y is positive, right? And the unit circle has a radius of 1. So what we're being asked is essentially, could this point be on this circle? No matter where it is, right, the radius of the unit circle is 1. So no matter how you want to draw it, the x and the y, right, if you draw it like this or like this, right, we're just thinking about different places where we're kind of looking at the radius, but the hypotenuse is 1. So what that means is it should be part of a reference triangle. If it is on the unit circle, then this triangle should exist, right? This triangle that I'm about to draw. Root 5 over 5 would be the x, and 2 root 5 over 5 would be the y, okay? So how can we check this? Well, again, if it's on the unit circle, then Pythagorean theorem tells us that when I square this and then square this and add it together, I should get 1 squared, or 1. So that's a way we can check, right? We know anywhere on the unit circle, oh, I should say for any point, x, y, on the unit circle, because of what we just talked about there, x squared plus y squared equals 1. So check if that's true for this point, right? That's how we can check if this is on the unit circle. So here we go. Let's see. What is root 5 over 5 x squared, okay, plus y, which is 2 root 5 over 5 squared. We're going to see, does that equal 1, right? Does it equal 1? Here we go. I might drop the color coding just for the sake of, efficiency here. So root 5 squared is just 5, and 5 squared is 25. So this is 5 over 25. And then 2 root 5 squared, well, that's 2 squared is 4, and root 5 squared is 5, right? Just multiplying 2 root 5 by itself. The 2 times 2 is 4. The root 5 times root 5 is 5. We can simplify 2. over 5 squared, which is 25. Does that equal 1? Okay, well, let's see. 5 over 25 plus, okay, we've got 5 over 25 plus 4 times 5 is 20 over 25. Does that equal 1? I mean, we can kind of see here already. We could reduce these fractions if we want, but also 5 plus 20 is 25 over 25. We've got a common denominator. So 25 over 25, does that equal 1? Yes, right? So yes, this point is on the unit circle. And there we go. We've just showed that that point must be on the unit circle. Otherwise, you couldn't draw this triangle, right? And we just showed that we can, right? So when the radius is 1, it's totally possible to have that x coordinate of that and that y coordinate of that. So that point must lie on our unit circle, right? If that triangle exists, then it exists along that, within the context of that unit circle there. Pretty cool, right? Okay, one more with the unit circle stuff before we really dive into the unit circle and its power for trigonometric ratios. All right, so here's one from a diploma. The point A, negative 2a, where a is positive, is the point of intersection between the terminal arm of angle theta, drawn in standard position, and the unit circle. Okay, we love to see that because now we know that the r in any ratio we set up will be 1. The value of a can be written in the form m over root n, where m and n are single-digit whole numbers, and they're asking us for what are the values of m and n. Okay, so essentially we need to figure out what a is, right? It's telling us that when we figure out what a is, we'll see that it looks like this thing. And then we just need to record what the values of m and n actually are when we write a in this form, okay? So let's, as is always a good idea, let's start with a little quick sketch because that can help us get our bearings pretty well for trigonometry stuff. Okay, so here we go. I'm going to draw out, let's just draw out the unit circle. So we've got a radius of 1, okay? And they're telling us a is positive, which means a, the x-coordinate, is positive, but then negative 2a, if a is positive, that means overall this y-coordinate is negative, right? So we've got positive x and a negative y. That means we're in quadrant 4, right? So this, wherever it is, okay, this point, I guess it would be a little bit closer to here since it's negative 2a and just a on the y and the x-axis, okay? This is the point a, meaning that here we are. This is the x value of that point a on the x-axis, and negative 2a on the y-axis. Okay, again, just meaning that this is at a y-coordinate of negative 2a. But what do we know? We know it's on the unit circle, so we know this radius, this hypotenuse of this reference triangle I'm about to draw is 1. So the x value is 1, the y value is, sorry, the x value is a, the y value is negative 2a. We can just draw a nice little reference triangle here. Okay, so this actually becomes, can you see where we're headed? This is looking pretty Pythagorean-y. Like we can solve it with nothing more than the Pythagorean theorem. Do you see what I mean, right? So often this comes down to like setting it up. Yes, that requires some Math 30 knowledge, but the solving portion is often just about saying, like the Math 30 part is saying, okay, how is this really just like some Math 10 or Math 9 even problem? Okay, this is just a Pythagorean theorem problem that we had to set up to see the Pythagorean relationship. Okay, so let's just write out what we know here. We know that negative 2a squared plus a squared will equal r squared. X squared plus y squared equals r squared, right? A squared plus b squared equals c squared. So notice, how many things do I not know in this equation? 1, and it's the thing I'm trying to find, a, right? So this should be a solvable equation. Here we go. Negative 2a squared, that's negative 2a times negative 2a. Well, negative 2 times negative 2 is positive 4, and a times a is a squared. So 4a squared plus a squared equals 1 squared is just 1. All right, now 4a squared plus a squared, combined like terms, that's 5a squared equals 1. And therefore, a squared equals 1 over 5. I'm just dividing both sides by 5 there to solve for a. And we're basically done. If I square root both sides, a is equal to the square root of 1 over 5. Well, the square root of 1 is just 1, and the square root of 5 is the square root of 5. Okay, can't go any simpler than that. 5 is not a perfect square, so leave it as root 5. Okay, now they didn't rationalize their denominator. Normally we probably would, but they told us not to, so we won't. Okay, so look, they told us that a could be written as m over root n. So they're asking us what's m and what's n when you write it that way. Well, now we can see m is just 1. N is just 5. So 1, 5. So to record this as a numerical response, you would just start in the first box, 1, 5. Remember, always left justify, so always start in the first box. If you don't need other boxes, that's great, but you just use them up left to right until you don't need any more. So we would put on our Scantron 1, 5. We would fully fill in the 1. We would fully fill in the 5. And there we go. Okay, just using the fact that the radius is 1 on the unit circle, and therefore, if you can draw a reference triangle on the unit circle based on a point that you know is on the unit circle, you can get, you can set up a Pythagorean theorem and calculate for lots of stuff. Okay, let's now get into what we can really do with the unit circle. So, again, what we're eventually building to is this. I'm going to show you it one more time so you can kind of see where we're headed, okay? Now, you can, by all means, I don't recommend it. I don't think you should. I think you'll actually have a much harder time if you do. You could memorize all this. You could think of it as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different pieces of information that you've just got to memorize. Okay, and that's just really, I mean, each of those pieces of information kind of really contains 3 more pieces of information, so 48 pieces of information. You could memorize them, sure. Okay, that's going to be tough, and it's going to lead to lower understanding in the end anyway. Okay, what I do instead of memorizing all of that is I understand like 3 things, right? Rather than memorizing 48 things, I understand 3 things, and I can build this all myself. Whenever I need it, whatever part of it I need, by understanding these relationships, we can get the unit circle, okay? The full unit circle all the way around, which again, we do need to know, but know as in understand is a lot easier than know as in have memorized, okay? So the first of those relationships that I'm talking about that I understand that lets me build the part of the unit circle I need is the special triangles, okay? Now we've seen these before in Math 20. They are the 30, 60, 90, or now that we're working with radians, we could also think of them as the pi over 6. That's 30 degrees, right? 30 is 1/6 of 180, so it's a 1/6 of pi in radians. Pi over 3, 60 is 1/3 of 180, so it's 1/3 of pi in radians, or 90. Again, 90 is half of pi, or 90 is half of 180, so half of pi in radians, okay? And the 45, 45, 90 triangles. So again, 45 is 1/4 of 180. 90 is half of 180, okay? So we call these triangles, where their names come from are the angles in them. And they're called special triangles, these 2 triangles. Special, all that really means is that they have some easily recognizable features, and they come up often enough that they're kind of worth just knowing those features, okay? And so we commonly use them as a quick reference, okay? So these, again, I will say, like, it's not about memorization, but there's a little bit of memorizing going on with just these, okay? Now, again, it's just 2 things to, and I'm using quotes here, to remember, because even with them, it's not like you fully have to always be able to memorize perfectly these, right? They're built on relationships that you know and understand, right? Like, for example, if you can even remember one angle and one side, you could use trigonometry and the fact that all angles in a triangle add to 180, or Pythagorean theorem to figure out the other sides, right? Like, for example, if you can remember that there's a root 3 and a 1, but you can't remember what the hypotenuse is, that's okay, because you could do, well, root 3 squared is 3, 1 squared is 1, so 3 plus 1 is 4, so the hypotenuse must be the square root of that, 2, right? See what I mean? If you can even just remember a couple things on each triangle, then you can construct the parts you might not remember in the moment, okay? So these are the 30, 60, 90, and the 45, 45, 90 special triangles, okay? Let's just talk about them a little bit before we look at them again. So the reason they're so powerful, remember from previous math courses, any triangles which have the same interior angles are said to be similar to each other, right? I mean, we've talked about this a few times today. If this angle is 30 degrees, okay, I could just as easily extend this and make a bigger triangle, okay? And this angle would still be 30 degrees. I'll just do it in a different color so you can see it, right? That triangle, that bigger red triangle, still has an angle here of 30 degrees. If this is 90, okay, this is 90, then this is 60. 180 minus 90 minus 30 would leave us with 60 there, right? So since they have the same interior angles, they might not have the same size. Like, again, maybe, well, this is, this is root 3 and this is 1. And maybe this is twice as big. Maybe this is 2 root 3 and this is 2. So individually the sides might not be the same, but the ratios are the same because these triangles have the same shape, right? Different size but same shape. They are similar triangles. So even though the sides aren't all the same lengths, this is the key takeaway, the ratios of their sides are still the same. And in trigonometry, what are we doing? Sine, cos, tan, cosecant, secant, and cotangent. What are all of those? They are ratios of one side to the other. And this is the power of these special triangles. Because for any angle with a reference angle of 30, 45, or 60, and there are a lot of angles that have those reference angles, right? In every quadrant, there's an angle with a reference angle of 30. In every quadrant, there's an angle with a reference angle of 45. And in every quadrant, there's a reference angle with an angle of 60. So that's 4 angles with this as a reference angle, plus 4 with this one as a reference angle, plus another 4. That's 12 angles right off the bat, okay? We can use the same ratios of our basic special triangles to find exact values because of this fact here. The ratios are still the same. So if any angle has a reference angle of 30, 45, or 60, if we can draw this triangle or this triangle, we can think about the ratio for that angle, right? Isn't that amazing? Because, again, if it has a reference angle of 30, even though, sure, the side lengths might be different, the ratio of the side lengths will be the same because it's essentially the same as this triangle. It's just a bigger or smaller version, but it has the same shape. So if you want to find, for example, I don't know, sine of 210. 210 has a reference angle of 30 degrees. 210 has a reference angle of 30 degrees because it is 30 degrees past 180. So right away, what can you do? You can use this triangle. If you want to find sine of 30, it's going to be equivalent to 1 over 2, right? And then you'd have to think about the sine using cast, but look how powerful that is, right? The ratio, the sine ratio of this angle, because it has a reference angle of 30 degrees, the ratio will be the same as this triangle's ratio. So if you can just remember these two special triangles, you've got 12 angles on the unit circle already. Notice, right? Look at these, 30, 45, 60, 120. That has a reference angle of 60. 135, that has a reference angle of 45. 150, reference angle of 30, and I could do this for them all the way around, right? 210, the one we just talked about, 30-degree reference angle. 225, 45-degree reference angle. So that's what I mean when I say I didn't ever in my life have I memorized all parts of this unit circle. I've thought about the relationships I need to get the part I need, and then I reference the appropriate relationship, whether that's a special triangle or a quadrantal angle, which we'll loop back to here in a second, right? Again, this 210 one has a reference angle of 30 degrees, so its ratio of its sides will be the same magnitude as our special triangle with the 30-degree here, the 60 here, like that. So sine of 210 will be something like 1 over 2 or 1/2. I'll have to think about cast for whether it's positive or negative 1/2, but that's the idea, okay? So the two special triangles give us 12 angles, and therefore every ratio for those 12 angles, right? So not even getting into the fact that now we know sine, cos, and tan, and cosecant, and secant, and cotangent, just by getting these two for 12 angles around the triangle. Just to quickly talk about them, a tip, I use the fact that 30 degrees goes next to root 3. That just helps me remember 3 for 30, 3 for root 3. So 30 is adjacent to root 3. And then we've got the 1 and the 2. Again, if you forget parts of it, you can always use the Pythagorean theorem or SOHCAHTOA even, or 180 degrees in a triangle to figure out the parts you don't remember. Okay, and I've been kind of talking in degrees here for now, but of course we could do this all in radians too, right? 30 degrees is just pi over 6. 60 degrees is just pi over 3, right? The 45 triangle is even easier actually, because it's just basically there were two sides here. We wanted to say, is there a special triangle we can use to reference for anything with a reference angle of 45 degrees? We said, yeah, the two sides would just be equal. Let's make them the easiest number to work with then. How about 1? Right? So it's 1, 1, root 2. And again, notice it's based on relationships you know. You can check it out, right? 1 squared plus 1 squared is 2, and the square root of that would be root 2. So the hypotenuse of this triangle would be root 2. Okay, 45 degrees is just pi over 4 in radians. It's the same triangle, it's just measuring its angles in radians instead of degrees. Okay, so these two special triangles show us that, okay, the sine of 30 degrees will always be 1 over 2, right? Whenever there's a reference angle of 30 degrees, the sine of that angle will be 1 over 2. Positive or negative 1 over 2 depends on which quadrant we're in, okay? The sine of 60, look, opposite over hypotenuse, root 3 over 2, okay? The sine of 45 degrees, well, opposite 1 over hypotenuse, root 2, which we would rationalize to root 2 over 2. Okay, cos theta, cos of 30, root 3 over 2, adjacent over hypotenuse. Cos of 60, adjacent over hypotenuse, 1 over 2, right? And that's all we do. Look at these ratios. Tan of 30, opposite, 1 over adjacent, root 3. Tan of 60, opposite, root 3 over adjacent, 1. So it's just root 3. Tan of 45, 1 over 1, 1. Okay, now go back and look at the reference, all the angles here on the unit circle. Okay, look at these points. Remember, x represents cos theta, y represents sine theta. Look at all of them. Those are all just the ratios we were just talking about, right? So again, we can pretty quickly, without having memorized this whole unit circle, for example, what will the sine of 330 degrees be? Well, what I recognize is that 330 degrees has a reference angle of 30. So I can think about this special triangle to get its ratio, right? What's sine of 330? Now all I've got to do is recognize that, okay, well, this is 30, and I know that this is like a special triangle. And if I can remember that, all right, 30 degrees, well, that is, I remember as 30 root 3, 3 for 30, 3 for root 3. Okay, and then this is 1, this is 60. Okay, again, if you forget any parts of that, if you can remember just a couple, you can figure out the other ones, right? All triangles add up to 180. So 180 minus 30 minus 90 is 60. You can use Pythagorean if you forget that the hypotenuse of this is 2. So what is the sine of 330? Well, it's going to be opposite, 1, over hypotenuse, 2. So sine of 330 degrees is, well, sine of 30 degrees is 1 over 2, okay, for this triangle here. But in 4 quadrants, we could recognize that, okay, but actually we're in quadrant 4, where where sine is negative, okay? Another way to look at it is that really this is a negative 1. So sine of 330 degrees is just negative 1 over 2. Notice, all I really used there was the special triangle and cast, okay? I definitely didn't have to say, good thing I've memorized the entire unit circle. And look at that. What is sine of 330 degrees? It's negative 1 over 2, okay? No memorization required, other than remembering the special triangle. So now you're probably noticing the other pieces we haven't talked about. We basically just covered all of these, all 12 of these, and how we can get them with our special triangles. We'll circle back to them again, but brief introduction there. It's using the special triangles, the 30, 60, 90, or the 45, 45, 90. That just leaves these ones. But these are just the quadrantal angles, right? 0, 90, 180, 270, or 0, pi over 2, pi, 3 pi over 2, 2 pi, okay? Let's remind ourselves of how those work. So the quadrantal angles, okay, called that because they separate one quadrant from another. So by remembering though, don't forget, sine theta is just y over r, cos theta is just x over r, and tan theta is just y over x. We can use points on terminal arms at those angles to find the ratios at these angles, right? If you have, again, any point on the terminal arm, well, then we can build a reference triangle and figure out that sine of that angle will be the y-coordinate of that point on the terminal arm over r, the radius, right? Or cos will be the x-coordinate over r, or tan will be the y-coordinate of the point over the x-coordinate of the point on that terminal arm. So we could technically use any point, but just to make the numbers even nicer to work with, let's just make it on the unit circle. Let's do a point of, like, let's look at if we're doing sine of 0, because we're looking at the quadrantal angles right now, right? Let's make our terminal arm have a length of 1 so that r is 1, okay? Now, think about this. What is x and what is a point that is on that unit circle and intersects with the terminal arm of an angle of 0? Well, it would be at 1, 0, right? It's all x, no y, right? To visualize here, look what's happening to the x and the y as I rotate to an angle of 0 and how they compare to r, right? At the x-axis, my terminal arm is just sitting at the positive x-axis here. So look, r is just getting closer and closer to being the same size as x while y becomes 0, right? Starting from up here, x grows, r gets closer and closer to just being the same thing as x. And it is the same thing when y becomes 0, right? That's why I said it's all x, no y there, right? The opposite happens when we go like this. We'll talk about that when we do 90 degrees, right? R is the same size as y when we're at 90 degrees. Okay, let's hop back to the notes here. Okay, so taking a look, right, again, here at an angle of 0 degrees, the terminal arm passes through the point 1, 0. So y over r, well, y is just 0. So 0 over 1 is 0. So sine of 0 is 0 because it's 0 over 1, right? Or 0 over any, whatever your r is, it's still going to come out as 0. Now, what would cos of theta be if 0 is our theta? Well, cos of 0 is going to be x over r. But x is 1 here, r is 1 here, right? And again, we could extend this beyond. We could say, what about if our terminal arm goes through the point 2, 0? Well, then x is 2 and r is 2, and 2 over 2 is 1. So cos of 0 is 1. Because x is r. Like I said, all x, no y, right? X is the same size as r here on the positive x-axis, which is where our terminal arm is if theta is 0, okay? And then tan 0, well, that's y over x, and y is 0. right? So this is what I mean when I say I think about some relationships and I don't really have to like memorize anything. I think, oh yeah, well, if the angle's 0, then the y is 0, right? So sine is going to be 0 because sine is y over r. Cos is just the same, x is just the same size as r. So x over r will just be 1. And tan will also be 0, right? So tan 0 is 0, cos 0 is 1, and sine 0 is 0. Let's rotate now to 90 degrees, like we just saw in that little animation I was showing, right? If we think about a point on the terminal arm of a 90-degree angle, so now I've rotated to 90 degrees, or pi over 2 radians, okay? Well, now it's all y, no x, right? The point on this terminal arm that we could think of is 0, 1, right? Or 0 doesn't really matter because sine theta is going to be y over r, and y is the same size as r here, right? So it's 1 over 1 in this case, which is 1. So sine of 90 is 1. Cos of 90, well, what's x? What's the x coordinate of the point on our terminal arm? It's 0. So 0 over 1 is 0. So cos 90 is 0, right? Sine 0 is 0. Cos 0 is 1. Sine 90 is 1. Cos 90 is 0. Okay? But it makes sense. It's not something to be memorized because, again, look what's happening between x. X shrinks to become 0 as I go from 0 to 90, while y grows from 0 into being the same size as r as I go from 0 to 90, right? Reversing it, x grows to become the same size as r. Y shrinks to become 0. Y grows to become the same size as r. X shrinks to become 0. Cool, right? So just thinking about those relationships can make this stuff a lot easier to pull out of your back pocket when you need it. All right, let's keep rotating now to 180. Now some things are going to get negative. We know that, right? Because now x is negative. So let's take a look here. Our x coordinate is negative here at a rotation angle of 180 degrees. Okay, maybe I should do that in green since everything's labeled green. Okay, so let's look. What's the y coordinate here? It's 0. So what is sine of 180 going to be? Well, sine is y over r, and y is 0. So sine will be 0. Sine of 180 is 0. Okay, what's x here? What is a point on the terminal arm? Well, we could use -1, 0, right? So x being -1. Now remember, r is always positive. So we've got -1 over 1, which is -1. So it is all x, no y, but the x is negative now, right? If I keep rotating, that x value is negative. And x is the same size as r, but x is negative and r is positive. Okay? So cos of 180 is -1. Tan of 180, once again, y is 0. So 0 over -1. Oh, that's not right. That should say, whoopsies, that's a mistake in the notes. I got to fix that. R is always positive. Oh, what am I doing? Sorry, I was thinking I was talking about sine. That's not a mistake. It is, because tan is y over x, and x is -1. But 0 over -1, still 0. So tan of 180 is 0. Okay? And then same logic, different outcome because we're in a different place now. If I keep going to 270, if I keep going all the way to 270, okay, what is the sine of 270 degrees? Well, now it's all y, but y is negative, no x, right? All y, no x. So we're sitting on the negative y-axis. A point on the terminal arm of 270 is 0, -1. So y over r could be -1 over 1, which is -1, right? X is 0 here, so cos is going to be 0 too. 0 over 1 is 0. Tan gives us something interesting here that I just realized I forgot to mention up here when we talked about 90. Tan is y over x, right? Since x is 0 here, well, we're dividing by 0. So go ahead and type tan 90 or tan 270 into your calculator. It's going to say error, undefined, because taking the tan of 90 degrees would require you to do, well, y over x, like always, which is 1 over 0 for 90 degrees, or 1 over 270, sorry, -1 over 0 for 270, which is undefined. We're dividing by 0. Okay, so those are the quadrantal angles. Okay, there's a quick kind of summary shown here. Okay, but that's where they come from. Notice I don't have those memorized necessarily. I mean, to be honest, I do because I've done a lot of trigonometry in my lifetime. Okay, but you don't need to memorize it. You understand the relationships, right? When in doubt, like, what is cos of 90 degrees? Do you have to know right away off the top of your head that it's 0? No, I mean, you might start to know these relationships quickly, but you can think about it. You can think, well, okay, 90 degrees looks like this, right? That's at the terminal arm of a 90-degree angle. So what's a point I could think about? X, Y. Well, how about, X will be 0 wherever I look, and honestly, it doesn't matter what we pick for Y because we know X is 0. So how about 0, 1? And if cos equals x over r, well, r is the same size as y here, right? The length of this is just all y, no x. So it's 0 over 1, it's 0, right? I didn't say, oh, good thing I've memorized that cos of 90 is 0. I quickly just thought about my ratios there, okay? To me, understanding that relationship is a lot easier than trying to memorize all this stuff, okay? So here is a summary of all of the stuff that we just talked about, okay? Now, should you memorize that? I mean, you're probably sick of me saying this at this point, but no, right? I do not suggest trying to memorize this table or the entire unit circle. It's much easier to understand those relationships, understand the two special triangles and the quadrantal angles. And then you can always construct any part of this table or of the unit circle that you need, right? I draw a quick sketch of the angle I'm looking for. I think about the special triangle that will let me think about that ratio, and then I use the cast stuff to tell me the sign of that ratio, right? So here's everything we just talked about, okay? That is where the unit circle comes from. But again, I don't just pull this out of my back pocket and know it right off the bat, right? Again, if I'm given what is tan of 270, okay, I don't go, oh, well, tan of 270 would be y over x, so negative 1 over 0, so it would be undefined, right? I quickly just think 270 is down here, right? So my terminal arm is going to look like that. I could take a point on it. How about x is 0, y is negative 1? So tan 270 would be y over x, negative 1 over 0, which is undefined, right? What would be sine of 270? Well, it would be y over r. Y is negative 1, r is just positive 1, so it would be negative 1. And notice, right, that is what is on our unit circle, but to me it's a little easier to think about than to memorize, okay? Now, you do need to know this. Don't confuse me saying you don't need to memorize it with me meaning that you don't need to know it, okay? You do need to know these and the ratios all the way around. But I suggest understanding those special triangles and using them as needed, along with the quadrantal angles, okay? That's a much easier way to do it, okay? If we use the special triangles and the quadrantal angles along with cast, we understand a few things and we can get all the same information that memorizing the unit circle would provide. Notice what's happening here, okay? All the unit circle is, look, here's our 30-degree special triangle, or our 30, 60, 90, I should say, right? Here it is in quadrant 2. Here it is in quadrant 3. Here it is in quadrant 4. I could do this for the 45-degree triangle as well, right? And the 60, well, the 60 and the 30 are the same triangle, but I'm just going to point out to you here, right? All we're doing is taking that 30-degree reference angle and that 30, 60, 90 special triangle, and we're essentially rotating it around, right, to construct our unit circle. So if you can just remember that this is the 30-degree, root 3, 1, 2, 60-degree, okay, then I can say, what is the, cosine of 210? Well, once I recognize that 210 has a reference angle of 30 degrees, and therefore I can use my 30-degree special triangle, I can say, what's the cos of 30? It's root 3 over 2. And then the only thing left to do, so I know that cos 30 is root 3 over 2, and then recognize that 210 is in quadrant 3, right? So cos of 210 Since it has a reference angle of 30 degrees, I can think about this triangle here and then recognize that, okay. So yes, cos of 30 is root 3 over 2. Cos of 210 is going to have the same value, but it's going to be negative because cos is negative in the third quadrant. Okay, and that is how we're going to approach these and solve them. Okay, and we'll use radians. I've been sticking to degrees just because I know this looks like a lot of information. I know we're probably a little more comfortable with degrees, but we can do it with radians as well, like we will in this next example here. All right, so for the indicated angles, state the coordinates of the point where the terminal arm intersects with the unit circle. Hey, the coordinates of the point where the terminal arm intersects with the unit circle, well, that just means, right, we know that that will be cosine of the angle, sine of the angle, for all the reasons we talked about. Since if it's intersecting with the unit circle, we have an r of 1, and therefore cos is x over r. It's just x, the x coordinate of that point. Sine is y over r, so y over 1. So it's just the y coordinate of that point. So that's really all we're being asked to find. Cos of this angle and sine of this angle. Then same for this angle. So let's go to work here. Let's see if our unit circle can help us out. Okay, so a 330 degree angle. First things first, let's get a reference angle. Okay, so that we can think about the reference triangle and actually start getting some trigonometric ratios with that reference triangle. So what is my reference angle here? Well, I didn't do a full 360. I'm in the quadrant 4, so I can do 360 minus 330, right? Here's a full 360. Take away 330, and I'll just be left with that green part there, the reference angle. So 360 minus 330 gives me that the reference angle is 30 degrees. Hey, you can have a little alarm set in your head. 30s, 60s, 90s, 45s. Those are special triangle angles, right? 30, 45, 60. Okay, so we can use a special triangle, right? That tells us we can use a special triangle. We can use the 30, 60, 90 special triangle. So do you see it here, right? Do you see how this is just our special triangle? Okay, right? There it is. So it has a reference angle of 30. We can think about this triangle here to start getting a ratio. And then we can use cast to get the correct sign. Okay, so this is root 3. You can use cast, but you can also just recognize that, okay, I'm using this special triangle, but really it's representing this thing in 4 quadrants. So this is a -1. That's one way to approach it as well. Okay, and this is a 2. So again, I always remember that the 30 goes with the root 3. Okay, one of the things I recommend when you're writing a test or you're writing the diploma, maybe the first thing you write down while it's fresh in your brain, draw your special triangles, because then you've got them ready to go whenever you need to reference them. Okay, this is 30, this is 60, but that's not our reference angle here, so we won't really need to think about that too much. Okay, but now this question just becomes, okay, what is the sine of 30? What is the cos of 30? And should it be positive or negative based on what quadrant we're in? Okay, so here we go. Sine, I'll say so, sine of 30 degrees, sine of my reference angle is going to be y over r, opposite over adjacent. Sorry, opposite over hypotenuse. So 1 over 2. Okay, what's cos of our reference angle? Well, cos of 30 degrees will be adjacent over hypotenuse, so root 3 over 2. Okay, we're almost done already. We just have to remember that we weren't actually using this 30-degree triangle. We're not trying to find the sine and the cos of 30. We're trying to find the sine and the cos of 330. So this is a reference triangle we can use to think about it, but we got to remember that we're actually over here in quadrant 4. We're in quadrant 4. So cos is positive, but sine is negative. Okay, so cos is greater than 0, but sine will be less than 0. And that just means that, okay, our point, well, here, putting it together, that means that sine of 330 is 1 over 2, but negative 1 over 2, because sine is negative in quadrant 4. Cos of 330 really is just going to be, it's positive. Quadrant 4, cos is positive, so root 3 over 2. Okay? And again, honestly, I kind of prefer to do it this other way for these type of questions, where I say, okay, yeah, this is a 1, but keeping in mind that we're really here, it's actually like a negative 1 for my y. And notice that would give us the same results, right? We would get sine of 30 would be negative 1 over 2. Negative 1 over 2, right? Sine of this angle is negative 1 over 2. Cos of this angle would be root 3 over 2, positive. Okay, both work. Both are valid. So we just got to put it together now. What is it that as point coordinates? Well, it's, put them together. Cos theta is root 3 over 2. Sine theta is negative 1/2. And there we go. That is the point where the terminal arm of 330 degrees will intersect with the unit circle. We used it to find cos theta and sine theta, and we know that cos theta and sine theta are the x and y coordinates of a point where the terminal arm of an angle intersects with the unit circle. Cool, right? But notice all I needed was this triangle, okay? I did not just pull those numbers out of my back pocket, right? But checking, okay, look, 330. 330, root 3 over 2, negative 1 over 2. Exactly what we got, just by thinking about that 30, 60, 90 triangle. Alrighty, let's try this one out. We've got 3 pi over 4, so we're working in radians here. Okay, we can do radians. Nothing wrong with radians. They're actually a great way to think about angles. Okay, first things first, let's get a reference angle. Okay, so that we can start thinking about the reference triangle, so that we can start thinking about ratios. Okay, because we know we need cos theta, sine theta. All right, so what would that angle be there? Well, again, right, we got 0. This is pi, right, because all the way around would be 2 pi. So if that's 0, that's pi. This is pi over 2, 3 pi over 2. Okay, so if we take a look, well, here's pi, right? This would be pi. And our angle, theta, is 3/4 of pi. So what's my reference angle here? Well, it must just be 1/4 of pi, right? It's the amount that we're kind of missing. So my reference angle is, we could figure it out by doing pi minus 3/4 pi. Pi minus 3/4 of pi, which is just 1/4 pi, right? So our reference angle, just going to go down here where I have a little more room, is pi over 4. Hey, like I said, have a little alarm in your head. Special angle. That's one of our special angles from one of our special triangles, right? Pi over 4 is equivalent to 45 degrees. Special triangle can be used. So here we go. Let's go ahead and we can do it. We can say, all right, what we can think about for this angle, the reference triangle we can think about is our special 45, 45, or pi over 4 triangle. Okay, now remember these two sides are equivalent, and we make it the easiest number it could be then, right? Because again, they're all just similar triangles anyway. That's why the ratios are all the same. So 1 and 1. And then what's this side? Root 2. You could just remember that, and you probably will eventually once you've done enough practice, because you'll use these so much. But if you ever forget, 1 squared plus 1 squared is 2, and the square root of that is root 2, using the Pythagorean theorem. All right, so here we go. I'm gonna, just to show you it a couple different ways for this one, I'm gonna do the other method from what I did last time. So I'm not even gonna rely on cast at the end. What I'm just gonna say is, okay, this is my reference triangle, but I'm going to recognize that I'm using it to think about this situation where x is really, it's negative, okay? And now we can just say, all right, so what is cos of 3 pi over 4? Well, it's adjacent over hypotenuse, right? X over r. It is negative 1 over root 2. We'll want to rationalize that denominator, so let's multiply by root 2 over root 2. That's going to give me negative root 2 over 2. Okay. And there we go. We've got cos of 3 pi over 4. Let's do sine of 3 pi over 4. Oh, color coding didn't work out here. Oh, well. It's all red. Okay, sine of 3 pi over 4. Well, we can use our special triangle. So opposite, 1 over hypotenuse, root 2. 1 over root 2. And again, we should rationalize that denominator. Root 2 gives me root 2 over 2. Whoops, make that red. Okay, positive root 2 over 2. Again, we can always kind of check with our cast. Does that make sense? Well, we know we're in quadrant 2, so we would expect sine to be positive, but cos to be negative. That's exactly what we got, right? And that's, again, we could have totally just ignored this negative here, just thought about that triangle, okay, and then used cast to tell us the signs. Or we can also, from the beginning, recognize that, okay, we're going to use this reference triangle, but really our x is like negative here because we're in quadrant 2. But either way, we get the same result. We get that the coordinates of a point that is on the unit circle and intersects with the terminal arm of this angle would be negative root 2 over 2 and positive root 2 over 2. And that was for the angle 3 pi over 4. Let's go take a look at the unit circle. 3 pi over 4. 3 pi over 4. There it is. Negative root 2 over 2, root 2 over 2, right? A negative x, a positive y. Okay, we did not have to know this whole unit circle off the top of our heads to do that. We just had to think about how does the 45-degree triangle kind of fit into the picture here, right? Well, if there's a reference angle of 45 in quadrant 2, like we just did, we can use that 45-degree reference triangle to get the ratios for that angle. Pretty cool, right? Very powerful. All right, just a note on notation here and how we sometimes represent things, okay? Sometimes we represent the coordinates of points intersecting the unit circle using the notation p of theta. So when you see that, it's just saying, what are the coordinates of the point where that angle's terminal arm intersects the unit circle? So just to go back to this, we could have said that p of 3 pi over 4 equals what we just found, negative root 2 over 2, root 2 over 2. That's sometimes a way we represent it, right? What are the points, what is the coordinates of the point where this angle intersects the unit circle, which is what we just found, okay? Oh, I guess it was in the notes here, right? We could have said that p of 330 was root 3 over 2 and negative 1 over 2, right? Or that p of 3 pi over 4. Ooh, I didn't rationalize my denominators there, but that's the idea, okay? So let's just try that out. More practice with this stuff, but also looking at that way of saying it. So determine the exact coordinates. Exact means no rounding, no decimals, right? Calculator's not really going to help you much here because the calculator is going to round any square roots. It's going to give you not an exact value. Okay, so determine the exact coordinates of each of the following angles' terminal arms with the unit circle. That's what this is saying, p of 5 pi over 6. Well, as always, before we get started on this, let's do a quick sketch because we got to figure out what 5 pi over 6 even really looks like before we can think about its reference angle and then eventually its reference triangle and therefore its trigonometric ratios and the cos theta, sine theta. Okay, so 5 pi over 6. Like I say, is that more than a pi or less than a pi? Less than a pi, right? By how much? By 1/6 pi. So let's just think about this. We've got 0, pi, right? Pi over 2, 3 pi over 2, and then all the way around would be 2 pi. Okay, so pi is like 6 over 6 pi, right? Well, we're not quite there. We're stopping we're stopping short of that. How short? Well, 1/6 pi, right? Pi over 6. Because 5/6 pi is 1/6 away from a full pi, a full 6/6 pi, right? Again, to do the math, we could say that, here, to find our reference angle, okay, our reference angle is just going to be pi minus, pi minus 5 pi over 6, right? Again, take away 5 pi over 6 from pi, and you're left with just that green reference angle there, which shows us that our reference angle is just 1 over 6 pi, or pi over 6, okay? Which is the same as 30 degrees, right? So just like you have an alarm in your head for 30, 45, 60 as being special angles, don't forget 30 is just 1/6 of 180. It's just pi over 6, right? 60 is just 1/3 of 180. It's just pi over 3. And 45 is just 1/4 of 180. It's pi over 4, okay? So our reference angle is pi over 6. This is a special triangle. We can use our special triangle to think about this. So I'm going to draw it out. We can use the 30, 60, 90. So yes, this is 30, but it's also pi over 6. Okay, pi over 6 radians. Okay, and I remember, again, this is 30 degrees, so it goes with it is adjacent to the root 3 side. Okay, and then this is 2, and this is 1. Sometimes called the count to 3 triangle because it's got a 1, 2, root 3. All right, so we want to find the coordinates where this terminal arm intersects with the unit circle. In other words, we want to find cos theta and sine theta, because cos theta will be the x coordinate, sine theta will be the y coordinate. So here we go. What is, and actually I'm going to do it again where I'm going to recognize that really this x here is negative root 3. We can use our special triangle, but I'm just going to recognize that it's in the context of this where x is negative. So what is cosine? Cosine of theta will therefore be adjacent over hypotenuse, right? So negative root 3 over 2. And again, if you're saying, but the hypotenuse isn't 1, r isn't 1, or sorry, r should be 1, not 2, because it's on the unit circle. True, but remember, they're similar triangles. They have the same interior angles. So even though we know we're looking for the point on the unit circle where the hypotenuse, the r, would be 1, we still know they have the same ratio because they're similar triangles. And that's why these are so powerful. So cos of that 5 pi over 6 is going to be negative root 3 over 2. Sine of 5 pi over 6 is going to be opposite. So 1 over 2. And there we go. That's it. That's actually it. Again, we could have also stuck with, not making that root 3 negative and just kept everything positive, and at the end thought about, okay, well, we're in quadrant 2, so sine should be positive, cos should be negative, exactly like we just found. So putting it together, p of 5 pi over 6, the point where it intersects the unit circle, will be negative root 3 over 2, 1 over 2. Those are the coordinates of the point where the terminal arm of 5 pi over 6 will intersect with the unit circle. Done. Alrighty, so next up we've got this. Find the coordinates of the point where negative 4 pi over 3 intersects with the unit circle. So a negative angle, so that, remember, that means we're rotating clockwise to make this angle, okay? But again, 0. You could even think of this now as like negative pi over 2, right? Negative pi, okay, if you like. So we've gone past negative pi. How far? 1/3 of pi, right? Negative 3/3 of pi would just be negative pi. And then we've got another negative 1/3 pi. So looking at it this way, our terminal arm will be somewhere like that. Okay, and that's negative 4 pi over 3. And we can kind of work out that our reference angle then, this angle here, is just pi over 3. Okay, again, to really show the math, we could say we're doing 4 pi over 3 minus pi, essentially, right? Because this is 4 pi over 3. Yes, negative, but reference angles are always positive anyway. So 4 pi over 3, take away the pi that's here, and you're left with the reference angle. So 4 pi over 3 minus pi gives us our reference angle, which, like we said, just means 4/3 minus 3/3 leaves us with 1/3 pi. Now, pi over 3. Is that something we can work with? Does that sound kind of special to you, right? 180 over 3 would be 60, and 60 is definitely one of our special triangles, right? So we're dealing with, if I draw it out here to kind of match what we're looking at, this angle is pi over 3, right? Which is 60 degrees, okay? Converted to degrees. So this is our 30, 60, 90 triangle, or our pi over 6, pi over 3, pi over 2 triangle, okay? So root 3 we know goes with the 30-degree angle, so this side is root 3. This is 1. The hypotenuse is 2. All right, now we just need to figure out cos and sine. Again, I might go with making this x negative here for this one, just recognizing that, yeah, we can use this special triangle to think about it, but we're really thinking about this terminal arm, this angle here in 4 quadrants, so I can just make that negative. Or again, you could just work with this triangle, just good old regular 1 root 3, 2, and then use cast to tell you that sine will be positive and cos will be negative because we're in quadrant 2. So cosine of our 4 pi over 3 angle will be adjacent over hypotenuse, x over r, negative 1 over 2, okay, x, negative 1, r, 2. Sine 4 pi over 3 will be opposite over hypotenuse, y over r. So positive root 3 over 2. And that's it. That's all we needed, right? We needed cos theta, sine theta to get those, sorry, just lost my train of thought there, to get the coordinates of the point where the terminal arm intersects with the unit circle, because those coordinates are just cos of that angle and sine of that angle. So p of negative 4 pi over 3, that's just the notation we use to represent the point where it intersects with the unit circle, is just cos, negative 1 over 2, sine, root 3 over 2. Okay? And again, we could go check all of these on the full unit circle. Okay? Negative 4 pi over 3. Negative 4 pi over 3 would be the same as positive 2 pi over 3, right? And look at that. Those are the exact coordinates we just found. All right, so go ahead and try these ones out. And again, it's good to mix in your practice as you watch the video lesson as well. So I would recommend taking some time to pause, practice, maybe do more than just, the A and B that are listed here. But at the very least, do these two while it's fresh in your brain to kind of get the hang of it. And then we've just got a couple more examples here to work through, and also looking at reversing this process and determining angles. But first, take a little practice break. All right, so here it wants us to determine the exact values for each of the following trigonometric ratios. Okay, so exact value means no rounding, right? Not like putting root 3 or anything like that into your calculator and getting a rounding thing. We want an exact value, okay? So first one up, tan of 11 pi over 6. First things first, we got to figure out what 11 pi over 6 looks like, so we can make a reference angle and a reference triangle and get the actual tan ratio from there, okay? So let's think about this. We've got 0, pi, right? Pi over 2, 3 pi over 2, and all the way around would be 2 pi. Now, 11 pi over 6. Where does that fit into this story, right? Well, 12 over 6 would be 2, right? So we're almost to 2 pi. We're just 1/6 pi short of a full 2 pi. So we can draw that out, okay? Close to a full rotation of 2 pi. That's where the terminal arm of our angle will lie. And what's our reference angle? I mean, we kind of just said it, right? It's going to be 1/6 pi. If we really want to show that, we can say it's 2 pi. Okay, take a full 2 pi, but subtract off 11 pi over 6, which we can see is just 12 over 6 pi minus 11 pi over 6. And therefore, our reference angle here is just pi over 6, right? Or 30 degrees. Again, pi over 6, 30 is 1/6 of 180. Okay, so pi is 180, so 1/6 of pi is the same as 30 degrees. Okay, so hey, special triangle, right? This is a special triangle. This is our 30, 60, 90, or our pi over 6, pi over 3, pi over 2 triangle. Okay, so here we go. Let's use that to think about what we're dealing with here. Now I know that I can think of it like this triangle where I've got pi over 6 or 30 degrees. Do you remember what goes next to 30 degrees? What's adjacent to 30? It's root 3. Right. And then this is 1. Again, we could think, well, in this context, though, we're really in the fourth quadrant, and that 1 is like a -1 for the y value. Okay. And then this is a 2. Okay, other way to look at it is, maybe not another way, but a reaffirming way is to say, okay, we're in the fourth quadrant, so what should tan be? Tan should be less than 0. Let's see if that happens, right? That's what we're predicting. Okay, we can kind of tell it will be. Opposite over adjacent is going to be negative. And so here we go. Tan of 11 pi over 6 is just going to be opposite, -1 over adjacent, right? Y over x, -1 over the square root of 3. Okay, now that's technically done, but we just need to rationalize it, okay, because we have a root 3 in our denominator. So let's multiply by root 3 over root 3 to get rid of that, and we'll see that tan of 11 pi over 6 is just -1 times root 3 is -root 3 over root 3 times root 3 is just 3. And there we go, rationalized denominator. Again, we could have also said, okay, let's just think about, let's not worry about the negatives just now, right? Let's just figure out what tan of 30 is, or tan of pi over 6 is, right? Just quickly show you what I mean. We could have just said, okay, well, tan of pi over 6 is 1 over root 3. But we're not thinking about pi over 6. We're thinking about 11 pi over 6, which is really in the fourth quadrant. We'll have the same size ratio, but might have a different sign. So we could have done it this way and then said, okay, and now I need to slap a negative on there because I'm actually thinking about 11 pi over 6, right? But we get the same result. So 11 pi, whoops, so tan of 11 pi over 6 is just -1 over root 3. And then we'd rationalize the denominator doing all that same stuff. Both are perfectly valid approaches. Whichever one kind of clicks with your brain more is fine with whoever's looking at it. Okay, let's do this one. Ooh, secant, one of our reciprocal ratios. That's exciting. Secant of 3 pi over 2. Ooh, that's one of our quadrantal angles, isn't it? Because we've got 0, right? Pi over 2, right? Halfway between 0 and pi. And then halfway between pi and 2 pi, we would find 1.5 pi, or 3 over 2 pi. Okay, so that's the angle we're dealing with, one of our quadrantal angles. This is 3 pi over 2. Now, again, let's think about a point on the terminal arm of that angle. Because if we can think about a point on the terminal arm of that angle, we can get the ratio, secant. Okay, well, how about, let's pick a nice easy point. How about we know x is what here? We're on the negative y-axis. So what is x? It's 0. What's y? I mean, it could be whatever we want, but let's just make it like -1 so that we can kind of think of this on the unit circle and make the numbers work out nicely, right? Now, secant. What's secant the reciprocal of? Careful. I know it starts with an S, so it's tempting to say sine, but they're kind of flipped here, right? Secant is the reciprocal of cosine. So secant, well, cos equals x over r, right? Secant equals r over x. So if we're thinking about using the unit circle here, which we totally can because the ratios are the same for these with that similar triangle aspect going on. So r, let's just make r 1, and then x is 0. Aha! So secant is 1 over 0, meaning that it is undefined. So secant of 3 pi over 2, secant of 270 is undefined. And there we go. Okay, we just determined the exact values. Again, all we were using there was our special triangles and our quadrantal angles, our special angles from 0 to 360, and then thinking about it in the context of 4 quadrants, whether that was by using cast at the end, or whether that was about thinking about it while working with our special triangles like we did there. Okay, same end result, same thought process. Notice what I meant, right? Understanding those couple relationships rather than memorizing 48 different things from the unit circle overall. Unit circle is great, but only if we understand the relationships it's built on. Okay? Alrighty, so the last thing we're going to talk about here is basically just reversing this thought process. What if you're given the ratio and asked to figure out what the angle must have been? And we really do. We just take this whole process and we put it in reverse, okay? So to determine angles when given a ratio, put it in reverse. You use a special triangle or a quadrantal angle to determine the reference angle, right? Usually we get our ratio from the reference triangle, from our special triangle usually, right? But now we're going to use the ratio to think about what the special triangle could have been, okay? If the ratio comes from one of these special triangles, that is. So just be on the lookout for, you know, the numbers that show up in our special triangles. Things like zeros, ones, twos, root threes, root twos. If you see those, take a second and say, hey, is this a special triangle? Because then you won't even need your calculator at all, right? You could use your calculator, but this is faster. Just draw a quick triangle, okay? If not a special angle ratio, so if it's not one of those like root 3 over 2s or 1 over 2s or zeros or ones, that's okay. You can still do it. You do it like, you know, you take the inverse trig operation of both sides like you've done a million times, right? If you have the ratio, take the inverse trig operation and that will give you the reference angle. Always use, this is super important, okay? Always use positive ratios when doing this, even if the ratio is negative, because we are just getting a reference angle, right? We're just trying to think about, all right, what triangle would let me think about this, okay? The problem with using the negatives is there's actually like 2 options for the negative. For all of these from 0 to 360, right? There's 2 places where every ratio is negative. And if you use that negative, it's only going to give you one of them. And you can't go further than that because now you don't know like exactly where you are and you can't properly place it. So we're just getting a reference, okay? We'll then use our knowledge of the 4 quadrants and cast and stuff like that to think about where the angle could be and what the angle is. Okay. Note that for reciprocal ratios, we mentioned this earlier, cosecant, secant, cotan. If you've got to if you need to do calculator stuff and it involves a cosecant, secant, or cotan, you'll first need to take the reciprocal of both sides, right? Because those are not on your calculator. Okay. And then from there, so notice we're kind of just working backwards through the process we've been doing. Okay, use the ratio to figure out what the special triangle is instead of using the special triangle to figure out the ratio. Okay, and then from there, place it into the 4 quadrants, right? Think about cast. If it's negative what quadrants would that ratio be negative in? If it's positive, what quadrants would that ratio be positive in, right? So use cast along with a domain to tell you which quadrants are possible. Now, like the default, I guess you could call it, is that there are 2 quadrants that are possible because, again, every ratio is positive in 2 quadrants and negative in 2 quadrants, right? They're all positive in quadrant 1, and then they're all positive in one other quadrant, right? Looking at cast, right? Cos is positive in these 2. Sine is positive in these 2. Tan is positive in these 2, and that goes for their reciprocal ratios as well, okay? Usually there's 2 possibilities, like I said, but again, there can be more or less depending on the domain specifications, okay? So for example, from 0 to 2 pi, there should be 2. From pi to 3 pi over 2, there's not going to be as many because we're only going from 180 to 270, okay? And then determine the angle itself based on the quadrant using those relationships, right? Stuff like 360 minus or 180 minus, whatever it is that you need to do. Let's try it out. So determine the possible values of theta on the given domains. It's saying if cos of theta is negative root 3 over 2, what is theta? Okay, and we're saying theta is between 0 and 2 pi. So it's within one rotation, what we would call the principal angle, principal solutions. Just from one rotation, a positive rotation from 0 to 2 pi. Okay, so root 3 over 2. I don't know about you, but that's making me think special, right? Root 3s, 2s. I know those show up in special triangles, so let's think about that. What triangle would have a cosine ratio of something like root 3 over 2, right? There's a negative. We'll worry about that when we put it into the 4 quadrants. But cosine, adjacent over hypotenuse. So I start there. I think about, okay, let's just think about a triangle, right? And it's going to have adjacent, like if I'm thinking about this as the angle, adjacent root 3 and hypotenuse 2, right? And look at that. We've already kind of started to build a triangle that we can think about. This has given us lots of hints, right? This is one of our special triangles. We've got the root 3, the 2. Do you remember what goes here? A 1. So what angle goes here? What angle goes there? That's the 30 degrees, right? But since we're kind of told to work in radians here, 30 degrees, but pi over 6 is kind of what we're going to use here. Okay, so pi over 6. So what we've just done, think about it. Any angle with a reference angle of pi over 6 will have a cosine ratio of root 3 over 2. So what we now know is that theta's reference angle is pi over 6. Okay, so find our reference angle. We kind of just did. Now, our reference angle is going to be the inverse cosine, we could say, of negative root 3. Whoops, sorry. I just made a big mistake. We're not going to include that negative. Remember, we're just looking for a reference angle. We're just thinking about, okay, what's the triangle I could think about? And then in the next step, I'll place it in the appropriate quadrant and think about whether it's negative or positive. But first, just getting our bearings by thinking about what that triangle's sides and ratios look like. Okay, so the reference angle is the inverse cos of root 3 over 2. From our special triangle, we know that that means our reference angle is 30 degrees. Or, I guess we're working in radians here, it's pi over 6 radians. Okay, that just came. Notice we're putting the process in reverse. Starting from the ratio, what special triangle would have that ratio for one of its angles? Now we know the reference angle is pi over 6. So next up, let's think about, okay, what angles have a reference angle of pi over 6? Okay, now there's 4, of course, because there's 1 in each quadrant. However, cast can narrow it down for us. So let's now use cast to think about where would cos theta be negative? Because cos theta here is negative root 3 over 2. Right? Well, it's not in quadrant 1. They're all positive. It's not in quadrant 4. Cos is positive there. So we are in quadrants 2 and 3. That is where our angles can be. Okay, so cos is negative root 3 over 2, meaning we must be in quadrant 2 or 3. So quadrant 2 and quadrant 3 are where we will have angles with a cosine ratio of negative root 3 over 2. Next up, we just got to figure out what those thetas are. So step 3, we'll actually find the angles. Okay, I guess you could have called this, finding the possible thetas, but really it's more like finding the quadrants. Okay, what quadrants are we in? So we now know we're in quadrant 2 and quadrant 3. So in quadrant 2, quick sketch is often helpful. We're looking for an angle with a reference angle of pi over 6 that's in quadrant 2. Okay, so this is pi over 6. This is pi, right? So how can we figure out theta? Well, it's going to be pi minus pi over 6. So 6 pi over 6 minus pi over 6, right? So our theta is 5 pi over 6. And you can always do a quick check. Take the cosine, make sure your calculator's in radians, but do the cosine of 5 times pi over 6, right? In fact, let's do that. Let's enter, whoops, wrong one. Oh boy. Sorry about that. Come on. Here we go. Let's do it. So let's make sure our calculator's in radians. It is. And we want to do the cosine of 5 times pi over 6. And look at that. Now that might not seem like much to you, but look, negative root 3 over 2, that's what it was, right? It's negative 0.86602545, which negative root 3 over 2, that's what we were trying to find, an angle where the cosine of that angle would be negative root 3 over 2. So quick way to check our work there, right? Cos of 5 pi over 6 is negative root 3 over 2. So that quadrant 2 angle is valid. However, there is another place, as we know, in quadrant 3, where the cosine of that angle would be negative root 3 over 2. So where is it? Let's think about it. We're going to go past pi into quadrant 3 now. Okay. And again, we know it has to have a reference angle of pi over 6. We're looking for the angle in quadrant 3 that has a reference angle of pi over 6, because that's the other place where this could happen. So what is our theta? Well, now we went past pi by pi over 6, right? So we're going to take pi and add an extra 1/6 of pi. So 6/6 of pi plus another 6 gives us 7/6 of pi. And once again, we can check our work. Let's do the cosine of 7 times pi. Whoops, close that bracket too early, over 6. Hey, that's negative root 3 over 2. Okay, so there's two answers here. Both of those angles have that cosine ratio. Okay, notice, right, follow these steps in the reverse order, and it's what we were just doing, right? Here we were given the ratio, and so we said what special triangle or, special angle would give us that ratio, and based on that, what's our reference angle, right? And based on that reference angle, okay, in which quadrants would angles with that reference angle be negative? Because our ratio is negative. So 2 and 3 in this case. And then it's just finding out what that actual angle would be, right? What is the angle in quadrant 2 that has a reference angle of pi over 6? What is the angle in quadrant 3 that has a reference angle of pi over 6? and using those relationships to figure it out. Pretty cool, right? I find these very satisfying. All right, let's try out another one here. Cotan. Cotan. So another reciprocal ratio is equal to 1 over root 3. Okay, so I see a 1, I see a root 3. I'm thinking, is this related to a special triangle? Okay, let's think about that. So we can use a special triangle to figure out what our reference angle must be. Because again, all all angles with the same reference angle as one of our special triangles can be used to find the ratio, right? So we're just reversing that process. Use the ratio to figure out what special triangle we can think about. Well, 1 and root 3. Let's think about this. We've got, okay, I'm just going to first, honestly, when we're given these reciprocal ratios, nothing wrong with them, but typically I find it a bit easier to turn it into its, non-reciprocal version. Okay, so what's tan of theta if cotan theta is 1 over root 3? Well, it's root 3 over 1, or just root 3. Okay, so what angle would have an opposite of root 3 and an adjacent of 1? Do you see how this is a special triangle, right? This is the 1, 2, 3 triangle, right? Root 3 goes with 30, so this must be 60, or pi over 3. And our hypotenuse is 2. Okay, so we're on a roll here. We've got our reference angle is pi over 3. Okay, our reference angle is pi over 3. So now we know we're looking for a triangle that has a reference angle, not a triangle, a angle that would have a reference angle of pi over 3. Now there are 4 angles that do that, 1 in each quadrant. But first things first, our domain is limited to just pi to 3 pi over 2. So we know we're in quadrant 3, okay? And that checks out because tan is positive, right? So normally we would say, okay, there's 2 places tan is positive, so we need to check quadrant 3 and quadrant 1. However, in this case, they just straight up told us we're just between pi and 3 pi over 2. So this is not a valid option for theta because quadrant 1 is not between pi and 3 pi over 2. So now we can just go ahead and say, all right, we don't even really need to figure out what quadrant we're in. The question limits the domain to the 3rd quadrant. So we are in quadrant 3 with a reference angle of pi over 3, right? We've got a terminal arm that looks like that, and the reference angle is pi over 3. We want to figure out what is the angle itself. What is theta? Okay, well, think about it. We're going past pi. How far? Pi over 3 past pi. So theta is just going to be pi plus pi over 3. Right? So 3/3 of pi plus another third of pi, that's going to give us 4/3 pi. 4 pi over 3. And you can check for yourself if you put in tan of 4 pi over 3, you'll get root 3. Okay? And there we go. So again, just kind of reversing the process there. Okay, of what we were doing with these ones where we wanted to get the ratio. Now we're given the ratio and we kind of work backwards to the angle. All right. And the last one here comes from an old diploma, and it's kind of a fun one. It mixes some logs in with some trigonometry, okay? So if log base 2 of k is equal to 1/2, and the cosecant of theta is equal to k, where 90 is less than theta, which is less than 270. So theta is between 90 and 270. Let's just think about that right now. 0, 90, 180, 270. Okay, so they're telling us we're between 90 and 270. In other words, we're just in quadrants 2 or 3. Theta is either in 2 or 3. then what is the value of theta to the nearest degree? Okay, well, let's think about this. If log base 2 of k is 1/2, and the cosecant of theta is equal to k, right? How can we figure this out? Well, we're going to need to know k, right? In order to figure out theta, we would need to know, if we knew what the ratio was, we could do all the stuff we just did to figure out what the angle is. But we don't know what the ratio is equal to. We don't know what cosecant of theta is. So maybe here we can figure something out. And sure enough, right, this is an equation where we can figure out what k is, because if log base 2 of k is 1/2, then remember, a logarithm just represents an exponential in a different way. So this is just saying that this to the power of this equals this. So 2 to the power of 1/2 equals k. So 2 to the power of 1/2 equals k. Now, 2 to the power of 1/2, remember, that's just the square root of 2. So k is just the square root of 2. And there we go. Now we found k. So what does that mean? It means that cosecant of theta is equal to k, but now we know k is just root 2. Now root 2, that shows up in some of our special triangles, right? A lot of our special angles. So we could work with cosecant. It's just, it's the reciprocal of sine, so it's hypotenuse over opposite. Totally possible to think about, okay, what triangle has a hypotenuse of root 2 and an opposite of 1, right? I do find it a little easier though, just because our brains are so used to sine, cos, and tan. If cosecant is root 2, well then sine is the reciprocal of that, 1 over root 2, right? Same end result, but you know, if you're fine with the cosecant, then that's great. For me, I like to just flip it so I can just think, okay, what triangle would have an opposite of 1, a hypotenuse of root 2? Or rather, what angle within a triangle would have opposite 1, hypotenuse root 2? Well, this is definitely looking like a special triangle now, right? This is the triangle we can use to think about theta. So we're wondering, what is this angle here that would have a sine ratio of 1 over root 2? Well, what side goes here? This is our 1. Whoops, sorry, no it's not. 1 and root 2. 1 and root 2. If you were really stuck, you could even use Pythagorean theorem here. This is actually our 45, 45, 90 triangle, right? 1, 1, root 2. Careful. That's a bit of a tricky one, right? 1, 2 versus 1 and root 2. So we've got a root 2 hypotenuse, meaning this is our 45, 45, 90 triangle. So now we know that whatever theta is, it has a reference angle of 45 degrees, right? Our reference angle has to be 45 degrees. It's the inverse sine of 1 over root 2, which is just, from our special triangle there, 45 degrees. Okay, so now the question becomes, what angles between 90 and 270 have a reference angle of 45 degrees? Well, let's think about this. Okay, let's think about this. We've got, okay, in quadrant 2, it would be this angle, 45. So whatever that angle would be, 180 minus 45, right? In quadrant 3, oh boy, that's a terrible 2. Sorry about that. In quadrant 3, it would be this angle. That would be the reference angle, and then it would be this, 180 plus 45, or 225, right? However, we can eliminate one of these because cosecant of theta was positive root 2, right? K we figured out was root 2, positive root 2. Sine theta is positive. It's positive 1 over root 2. So if we think about it, cast, right? Sine is only positive in quadrants 1, which is eliminated by our domain, and quadrant 2, okay, which is in our domain. Quadrant 3 cannot be. It can't be the quadrant 3 option because sine would be negative there. We know sine theta is greater than 0. So it can't be in quadrant 3. So that means our theta is the quadrant 2 option here. So how do we figure that out? What is theta itself? Well, we already kind of said it, right? This would be 180. So we've got to do 180 minus 45 degrees. Theta will be 180 degrees minus 45 degrees, and it looks like theta is just 135 degrees. There we go, 135. So we would fill in on our Scantron, right? 135, 3, 5. Okay, so same exact process, it's just an extra little flavor thrown in there where we had to use a logarithm to first figure out what cosecant theta was even equal to. But from there, same process. If cosecant theta is root 2 and therefore sine theta is 1 over root 2, well, what angle would have an opposite of 1 and a hypotenuse of root 2? Well, that's our 45-degree reference angle, right? And then thinking about, okay, well, what angles in quadrants 2 and 3 would have reference angles of 45 and give us a positive sign? Well, the only answer then is the one in quadrant 2, and 180 minus 45 to get the angle itself gave us that 135. All right, so that wraps up lesson 2 for trigonometry. Go ahead and get some practice with this stuff if you haven't been pausing and working on the practice throughout. But yeah, reach out as always with any questions or concerns, book a meeting, send an email, whatever floats your boat. But yeah, get some practice with this stuff because having it down pat makes the future of trigonometry for us a lot smoother, right? Getting down those relationships and those ratios and thinking about how they're all connected. Alrighty.